Japan. We understand that the semiconductor value chain is one of the most important value chains in the world. Globally, everything is moving toward advanced electronics, artificial intelligence, as well as electromobility. And the semiconductor is by far the basis for all this new movement and industry. So we understand that, and through our ambassador and our embassy in Japan, as well as the effort of our educational sector, we'll be prepared, as well as through the sharing of knowledge of Japanese universities, as well as companies. Baja California is the state that is the window to Asia, from Mexico to Asia. And that is very important to acknowledge. We would like to celebrate this. We would like to congratulate everybody in this seminar, as well as give a warm invitation to everybody from Japan that is participating to join us in Baja California and experience firsthand what our state and what Mexico can offer. Thank you very much, and have a great, great seminar. Thank you.
Thank you, Rodolfo. It is also our pleasure to introduce Marta Lobo Rodriguez, General Coordinator of Linkage and Academic Cooperation at the Autonomous University of Baja California, in representation of Baja California Academy. Her experience in strengthening academic partnerships and promoting international cooperation will provide valuable context as we begin today's discussion. Marta, welcome.
Thank you. Good morning in Japan, good afternoon in Baja California. I will speak in Spanish, and afterward, Araceli Sosa will assist me with the translation. Estimados colegas, participantes y público que nos siguen en redes, les saludo con mucho gusto. Saludo con gusto a Rodolfo Andrade, a Takeaki Sakurai, Director of the Office of Global Initiative, the University of Tsukuba. It's a pleasure to greet you and thank you for making this possible. Embajadora Melba Pría, gracias por acompañarnos a este evento tan significativo. Es un verdadero placer y agradezco a las universidades que me hayan dado la oportunidad de hablar en representación de las 5 universidades de Baja California que participamos en este proyecto. Hoy nos reunimos para dar inicio a este seminario en donde vamos a abordar 2 áreas claves para Baja California, que son los semiconductores y la inteligencia artificial. Este seminario es una excelente oportunidad para construir un puente entre las universidades, en la Universidad de Tsukuba y las universidades de Baja California, que me voy a permitir mencionar, que es el CETIS Universidad, la Universidad Tecnológica de Tijuana, la Universidad Iberoamericana y el Grupo Educativo 16 de septiembre, además de la Universidad Autónoma de Baja California, a quien me toca representar. Colaboraciones como esta son muy valiosas, no solo para compartir conocimientos técnicos, sino para fortalecer los lazos entre nuestras comunidades académicas y culturales. Al compartir conocimientos e ideas, estamos sentando las bases para un futuro lleno de oportunidades entre ambas naciones. Me gustaría agradecer especialmente a nombre de las universidades a la Secretaría de Economía e Innovación de Baja California por el fuerte apoyo y compromiso para hacer este evento posible, y por supuesto un agradecimiento muy especial a la Embajada de México en Japón por su ayuda en hacer que este evento sea una realidad y que sea el inicio de una gran colaboración. Es increíble ver cómo, a pesar de las grandes distancias que tenemos y esta diferencia de horarios, podemos trabajar juntos hacia metas comunes en el tema de investigación y tecnología. En un mundo tan cambiante que estamos viviendo, la colaboración internacional es más importante que nunca. La mejor manera de mantenernos a la vanguardia es trabajando juntos. Nosotros como universidades tenemos un papel crucial preparando a las próximas generaciones de científicos, ingenieros y líderes que seguirán avanzando en las tecnologías de manera responsable y ética. Me gustaría también agradecer a la Universidad de Tsukuba por la oportunidad de colaboración con las universidades de Baja California, a quienes también reconozco y agradezco toda la colaboración para que este seminario sea una realidad. Estoy convencida que esto será solo el comienzo de muchos proyectos y colaboraciones que beneficiarán a nuestras instituciones. A todos los participantes que nos siguen a través del Zoom y las redes sociales, les deseo que aprovechen al máximo esta oportunidad para aprender, compartir y colaborar. Las ideas y conexiones que creamos hoy conducirán a los avances de mañana. Trabajemos juntos para dar forma al futuro de los semiconductores y la inteligencia artificial. Muchas gracias y que disfruten el seminario.
Dear colleagues, participants and esteemed participants, it's a real pleasure to be here speaking on behalf of the universities of Baja California. Today we come together at an exciting time when two key areas, semiconductors and artificial intelligence, are merging to drive innovations that will shape our future. This seminar is a fantastic opportunity to build a bridge between the University of Tsukuba and the universities in Baja California. Collaborations like this are so valuable, not just for sharing technical expertise, but also for strengthening the ties between our academic, cultural, and economic communities. By sharing this knowledge and ideas, we're laying the groundwork for our future full of opportunities. I'd like to give a special thanks to the Baja California Ministry of Economy and Innovation for their strong support and commitment to making this event possible. And of course, a big thank you to the Mexican Consulate in Japan for their help in making this collaboration happen. It's amazing to see how even across great distances, we can work together toward common goals and research and technology. Artificial intelligence and semiconductors aren't just tools, they're powerful drivers of change. With them, we can improve efficiency, solve complex challenges, and push industries forward. Here in Baja California, we're already seeing how these technologies are impacting areas like manufacturing, healthcare, and renewable energy. And the future looks even brighter. In today's fast-changing world, international collaboration is more important than ever. The best way to stay ahead is to work together. Universities have a crucial role to play, preparing the next generation of scientists, engineers, and leaders who will continue advancing these technologies in a responsible and ethical way. I'd like to thank the University of Tsukuba once again for the partnering with us and for their leadership in these fields. I'm also grateful to the universities in Baja California for helping make this event a success. I believe this is just the start of many exciting projects and collaborations that will benefit both our institutions and societies. To all the participants, make the most of this chance to learn, share, and collaborate. The ideas of connections we create today will lead to tomorrow's breakthroughs. Let's work together to shape the future of semiconductors and AI. Thank you.
Thank you, Martha. Now we're glad to introduce Mr. Takeaki Sakurai, Director of Office of Global Initiatives from Tsukuba University, who will share some words with us. Mr. Sakurai, please go ahead.
Hi, good morning and good afternoon, ladies and gentlemen. I'm Takeaki Sakurai, the Director of the Office of the Global Initiatives, University of Tsukuba, Japan. On behalf of the University of Tsukuba representative, I want to say the huge thanks to all of the organizer, the governmental office of the Baja California, and the consulate of the Mexico in Japan, and the BC Academy, and the other Baja California universities. I'm really thanks to your hospitality. 30 years ago, I was young, and I was the graduate school student to start about the research on semiconductor. And my neighbor laboratory, they deal with the artificial intelligence. At that time, I cannot imagine that today's evolution of the automation, that the vehicle and the artificial intelligence, the based programming, and the so dense, the packed semiconductor, the chips and so on. So now we can watch about today's evolution, but we need to think about 30 years the later. That means about the future technology. Can you imagine about it? So to realize about the bright future, So we need to talk together the overcoming about the wall of the nationality and the place, and to build about the partnership to encourage to be a new challenge on technology. So I hope that today's the workshop is the starting point for the collaboration between the University of Tsukuba and Baja California. Muchas gracias. Thank you.
Thank you, Mr. Sakurai. Your insights are invaluable, and we appreciate your contribution on today's discussion. And to conclude the welcoming remarks, we are very honored today with the presence of the Embassy of Mexico in Japan. Mrs. Melba Pria, Ambassador of Mexico in Japan, will share with us an important message. Ambassador Pria, welcome. I think the microphone is off.
Okay, can you hear me now?
Yes.
Good morning, Japan. Good afternoon, Baja California. For the Mexican Embassy, it's a real pleasure to have you all here. When in April, Nagata-san and Ikeda-san received the Baja California University delegation and our friends from the government, we would not have imagined that it was relatively easy to make these universities work together. So we really thank everybody for being here today, for gathering to exchange knowledge and opinions on these two very interesting topics that are highly relevant for today's world. Doctor was just saying about 30 years ago when he was young. 30 years ago, these would have been impossible. Being in a Zoom, 20 people from two very, very different regions. And today it's our everyday tool. So how do we think about the future in today's world that is much more changing than 30 years ago? So for Tsukuba University, the universities in Baja California represent that ideal connection between Mexico and the North American economy and industrial market. Baja California is not only the closest state or prefecture to Japan, it is also the closest Mexican state to the California high-tech industry. So Baja California has a highly trained and educated population. We have around 1,500 to 2,000 graduates of universities of Tijuana that are engineers. The semiconductor sector in Baja California is by far the highest competitive hub within Mexico. And the companies in Baja California, not only the Japanese companies, also other companies from other, let's say, capital are the first and fastest growing in Mexico to implement artificial intelligence. So these collaboration between Tsukuba universities, the Ibaraki companies, and the Baja California universities can be really, really interesting. Tsukuba University has already recognized the potential of Mexico. They have been participating since 2011 in the 6th edition of the Mexico-Japan Rectors Meeting. So, and they will be hosting the 7th summit in 2 years. So Tsukuba University is a great partner in promoting academic mobility, but also exchange of students, of postgraduates, of teachers. And I am very excited to see this. A small note about something else. Claudia Sheinbaum, our first woman president, announced during her inauguration speech that the current administration will continue Plan Sonora, which aim to promote the northern Mexican region through development of key industries and renewable energies and semiconductors. And just a couple of days ago, Sonora signed an agreement with Taiwan to build a very big semiconductor premise in Mexico. So Baja California is a state that will necessarily benefit and move even further from these issues. So I'm certain that these exchanges, joint collaboration and research will be coming out of this first seminar. Just to tell you that you can rest assured that for the Mexican Embassy in Japan, this is a priority, and we will continue the support for everybody that needs it. I am sure that this is a win-win situation for everyone, for Tsukuba University and the 5 universities of Baja California that are here today. Thank you very much, and this is the Embassy of Mexico. Gracias.
Thank you, Ambassador. Thank you, everybody, for your valuable insights and the work that you have shared with us. Now we're ready to kick off our seminar. The program will be divided into 2 segments. First, the semiconductors, with the participation of 5 representatives from Tsukuba University and 5 representatives from Baja California Academy. And the second segment will be focused on artificial intelligence, also with the participation of 5 representatives from Tsukuba University and 5 representatives from Baja California Academy. For the semiconductors segment, which is the first one, I would like to invite Takeaki Sakurai, Director of the Office of Global Initiatives at Tsukuba University, and Juan Terrazas, Engineering Director at CETES University, to moderate the discussion on this topic in both regions. I think the microphones are off.
Okay. So this is wonderful, the discussion, the topic. And then firstly, we want to invite about the 4th speaker from the semiconductor side, and Professor Akira Uedono. He is one of the leader on the semiconductors at the Tsukuba area. Tsukuba is the science city, and we can see about many national institutes located the same place. In our field, the Advanced Industrial National Technology and the National Institute of Material Sciences and the Photon Factory. This is a synchrotron factory. This is the main location of the collaboration in the Tsukuba area for the industrial and the academic researches. And he is now the organize some of the collaboration. So the Professor Uedono, would you show your face and start about your presentation?
Okay, thank you very much. Can you hear my voice?
Yes.
Okay, let me share my screen. Where is my screen? This is my, no, this is not my screen. Wait a minute. Maybe this one. Maybe this one.
Yeah.
Can you see it?
Yeah, I can watch your screen, and you are the faces in the screen. Okay.
Thank you very much. Thank you very much for introduction, and thank you for having me today. That is a great honor for me. So in this presentation, I'm going to talk about first strategy of semiconductor research and development in Japan, and the role of research facilities in Tsukuba City for future semiconductor devices. So let me start. So first of all, let me start from bad news. Very, very bad news. Japanese share in the semiconductor market has been decreasing since 1990. Actually, the 1990 Japanese share was 50% world market, but nowadays 50% to decreasing less than 10%. So this is actually a very bad situation. And recently, 2021, Ministry of Economy, Trade, and Industry in Japan finally recognized the situation. So they are going to they made a strategy to revitalize Japanese semiconductor activity recently. But first of all, let me talk about their understanding of present situation. Semiconductors are the important foundation to support digital society, such as 5G, big data, AI, IoT, automated driving, robotics, etc., etc. their strategic technology of vital importance directly linked to national security. Well, national security. So that is why politicians finally working on this issue. So Japanese government made 3 strategies in order to revitalize the semiconductor activity in Japan. The first one is step 1, enhancement of basic production capacity for IoT. So as you may know that a lot of factories, semiconductor factories now working in Japan. And step 2, realization of next generation semiconductor technology through Japan-United States collaboration. And step 3, the future technology infrastructure through global collaboration. This is very important topic, and we, Japanese university scholar, greatly related to step 3. So let me talk about step 3 in more detail. So step 3 is actually the project framework for next generation semiconductor devices. Actually, that is a beyond 2 nanometer rule semiconductor device or beyond the 2 nanometer semiconductor device. And Sakurai-san, can you see my screen?
Yes, but this is the frozen. So we cannot see about the second slide.
Okay, so let me second screen. Okay, so frozen. Okay. Wait a moment. How about this? No.
Yeah, now that it is working.
Okay. Frozen. Wait a moment. Now I'm going to check the station. Okay, so you can see my screen, right?
Yes.
Okay. So in that case,
But we cannot see about, yeah. Now that we can see about your slide.
but this is the presentation.
Yeah, this is not
Wait a moment. Sorry for the trouble. What can I say? What I can do for wait a moment. This is my program. Okay. First, let me check camera. Okay, first, let me check. Okay. So this is this, and let me do it again. No, doesn't work. I'm very sorry, but please let me do it this one. Okay. Now, Gamen 2, 4. How about this? Not this one.
now it's okay.
Wait. Gamen 4, 2, 4. Nope. Where's my?
This is step 3 that we can see about the slide.
Okay. Is this presentation file? Presentation mode?
Yes.
But it must be small screen, right?
No. It's big.
Okay, so I'm not sure the trouble, but can you see this second screen?
Yes.
Can you see second?
Yes.
Okay, and can you see my laser pointer?
Yes.
Great. I'm sorry for that trouble. Sorry. So as I said, that the Japanese share in the semiconductor market has been decreasing since 1990. And therefore, the Japanese government decided that the basic understanding present station. So Japanese government are going to set up a strategy with 3 steps. Step 1, step 2, step 3. Now let me talk about step 3. So step 3 is a project framework of next generation semiconductor devices. And the major player is a Rapidus and Leading Edge Technology Center, so-called LSTC. So Rapidus is actually the companies founded 2022 and invested by 8 major Japanese companies: Kioxia, Sony, SoftBank, Denso, Toyota Motor Corporation, NEC, etc., etc. They are now making a big fab in Northern Ireland, Hokkaido, and I suppose that they are going to fully functionalize up to 2026. So this is a fab. So another player is a Leading Edge Technology Center, so-called LSTC. LSTC is a research center of Rapidus. The role of LSTC are R&D for design technology and R&D for equipment and materials. But LSTC is consisting of universities and national research laboratories, such as Hokkaido University, Tokyo University, Tsukuba University, Tokyo Institute of Technology, etc., etc. And talking about the national research laboratories, they are AIST, NIMS, KEK, RIKEN. So as you can see, Tsukuba University is here, AIST located in Tsukuba, NIMS located in Tsukuba, KEK located in Tsukuba. And the pilot line of Rapidus publication line will be set up in AIST and NIMS. So let me explain the relationship between location of those facilities. Tsukuba University is here, and the National Institute of Advanced Industrial Science and Technology, AIST or IST, here, and the National Institute of Material Science, NIMS, here, and High Energy Accelerator Research Organization, KEK, here. So we are very close. So we collaborating and compile their resources, our resources for R&D to support creation of knowledge and their application in industry. So this is not only the collaboration of research, but also we are exchanging the human resources. For example, some of researchers who belong to AIST, KEK, NIMS, are the professor of Tsukuba University. And the professor of Tsukuba University could be the researcher in those facilities. Well, actually, I am a guest researcher of AIST, guest researcher of KEK, guest researcher of NIMS. So we are collaborating with each other. So what I want to say that Tsukuba is a center of semiconductor research and development in Japan. However, but AIST and NIMS KEK University Tsukuba Alliance is not only limited electronics and manufacturing, but also spread into many fields, such as energy and environment, life science and biotechnology, information technology, and material and chemistry. So I have a proposition. When you consider the collaboration with the University of Tsukuba, it would be nice if you could use your pre-existing relationship or consider also collaboration with AIST, NIMS, and KEK. And I'm very happy to help you to collaborate with such facilities. Well, I think I forgot self-introduction, so let me do it just right now. I'm a material scientist, and I'm interested in the defect behavior in solid-state materials. My major technique to study defects is a positron annihilation spectroscopy. A positron is an antiparticle of electron. So using positron, we can study the defects in the materials. For example, detectable defects ranges from monovacancy to open pore. In my opinion, it's high sensitivity and non-destructive technique. There is no restriction of sample temperature or conductivity, and the detection of defects in the subsurface region is possible. So application of the positron annihilation is pretty wide. We can study semiconductors, metals, insulators, polymers, living materials, etc., etc. So if you could interested in this technique, please go to ORCID and hit my family name, and you will find my work there. So that's all my talk. Thank you very much, and muchas gracias.
Thank you, the Professor Uedono. So today's schedule is so tight, therefore the question, we will have the final discussion session. So thank you. So I want to introduce the next speaker, the Professor Kaoru Toko. He is the associate professor and now working on the flexible electronics. The flexible electronics is the important technique for the integrate for the Internet of the Things IoT devices and the mobile one. So he developed about a new technique for the low temperature growth of the good semiconductor thin films. So Professor Toko, would you start about your presentation? 床先生、マイクが。Wait a moment. また声聞こえないですね。Rita, please wait a moment. Okay, the Toko sensei, would you change about the order of the presentation? Firstly, we will have the Professor Hironori Okumura first, and then move to the Toko sensei's work. Okay. So sorry, due to the problem for the microphone, then I won't switch about the presentation. So next speaker is the Professor Hironori Okumura. He is the assistant professor on our institute. His background is widely of semiconductor and the specialty of the semiconductor, the sensor, like as radiative, the light and element. So today, he want to talk about the power electronics, in particular for the gallium-203, the gallium oxide devices. Professor Okumura, would you start your presentation?
Can you hear me?
Yes.
Okay. Can you see my slide?
Yes.
Okay, let's start talk about. Okay, so thank you for your introduction. Thank you for inviting this seminar. I'm working on the power device and using the wide bandgap materials for that. So the power devices using the new materials is very important currently now because now carbon dioxide issue is very serious for all the human beings. So now most of the devices using the silicon. The silicon is an excellent material for the electronic devices. But for the power, for example, recently the electric vehicle is under industry and some equipment is needs some more power energies. So that we need the high efficiency devices. For the high efficiency devices, the silicon is not excellent materials. So then for the more the high efficiency devices, we need the new materials is very important for the downsize and the low loss switches. For example, the silicon is excellent for the currently used every devices, every equipment. So the electric vehicle and the train and some solar cell changing or power AC/DC inverter and the DC/DC converter and some equipment. Recently, the silicon carbide is using for just starting to use for these power devices. So for example, for the electric vehicle, the Tesla 3 and some Toyota's vehicle, previously the silicon device is using the hybrid car. So the silicon is it's for the inverters. If we use the silicon carbide materials, we can use a smaller inverter and we don't need the cooling systems. So because the wide bandgap materials is very strong for the high temperatures. Okay, so the high efficiency and the downsizing and so that these materials are very important for the futures. So the Tsukuba University was four professors for the silicon carbide power electrode devices and materials from the material to the package. And for the silicon carbide using that in Japan is a train and some of the industry areas. Okay. So the issue of the silicon carbide current issue is the cost. So for the more future, so we are focusing on the new materials for low loss, low cost, and high efficiency materials. So that candidate is gallium oxide. The beta gallium oxide is can be grown by the melt-based method like the silicon. So silicon carbide and gallium nitride and other materials is high pressure and high pressure and high temperature growth method. So the cost is increased, but the gallium oxide can be grown the melt-based method. And now in the large size and the low cost is available. And the epithelial growth temperature and process temperature also much smaller than the silicon carbide and gallium nitride. And the critical electric field, that parameter is also very high. So compared with the silicon carbide and the gallium nitride. So that's this parameter is very important for low loss switching. So that low on resistance. So we can make this means we can make the high efficiency devices. So the gallium oxide is a very excellent material for the high efficiency and low cost materials. So currently, the novel crystal technology in Saitama Prefecture in Japan. So this company can provide gallium oxide materials and fabricate some Schottky diode. So currently, the 4-inch size material substrate can be obtained, and 6-inch size is developing. And TNSC is this company also in Japan. So this company can make the growth systems. So this company recently 6-inch size machine can be used. So now we can make the 6-inch size of materials and epitaxial growth can be obtained. And in our laboratories, we have the two growth methods, the molecular beam epitaxy and the metal oxide vapor phase epitaxy CVD methods. So that in our laboratory, so we can purchase from the novel crystal technology, and we can go the two methods and epitaxial layers and N-type doping also available. And here is a growth system. For example, is a MB machine. So MB machine can be grow the gallium cell and the dopant cell and the aluminum cell and the oxygen plasmas. So using these cells, so we can grow the materials for the substrate use. And here is the, for example, growth of the aluminum gallium oxide. Here is aluminum cell. The aluminum gallium oxide layer on the gallium oxide substrate here. For example, this one. And for the device fabrication, is Tsukuba area is very excellent because very nice open facilities. There are many here. So the previous is Uedon Sensei introduced about the Tsukuba City. Here is a train station. Here is Tsukuba Station. And the north side is the Tsukuba University. From the by bike is around 20 minutes from the station. And over there is a KK here. And the south side is Nimus and Ace here, so that we can these three university and the research center has open facilities, and some company also using the ICE and the Nimus open facilities, and especially the Nimus is excellent. Has excellent open facility here as a very new equipment here and the TM and the process resource. So using the in our laboratory, so we grow the sample in our laboratory. After that, so using these equipment, so we fabricate the devices. Here is an example is a collaboration with MIT and some universities. We got from the parties substrate, then we grow the gallium oxide, and the gallium oxide is N-type is a tin dopes materials, and we fabricate the modified FET structure here. So we demonstrate fast demonstration of the here is not fast demonstration, but we fabricate mod FET. And we also the first demonstration of aluminum gallium oxide channels that transistor here in Tsukuba. And here is a collaboration with ROM, Japanese company, power device company. So here is a Schottky barrel diode, the gallium oxide. And we achieved a very excellent performance using that. This one is ideality factor is almost 1 and the breakdown voltage is over 400. So we fabricate a low loss and excellent device power devices. And so let me summary my talk is we can make from the epitaxial growth to the device fabrication, and we can collaborate with some research centers. And now we have the many international and industry collaboration. It's ROM, DORA, TEL, and NCT, and MIT, BFL, and some of the European universities. So thank you for attention.
Thank you for the Professor Okumura. The schedule is a little bit behind, therefore we have to move to the next speaker. But thank you, the Okumura Sensei.
Thank you so much.
And the point is our institute has the many power semiconductor based laboratory, and we have the laboratory working on the silicon carbide based devices and the characterization of the material property of the silicon carbide. But also we have the many facility of the oxide material and other power device material. Therefore, we can have some of the specialty on the field of the wide gap semiconductor and also the power devices. And this is what we can do at the Tsukuba area. Okay, so the next presentation will be given by the Professor Kaoru Toko. Please try again about the microphone.
Yes, and
okay,
I'm ready, Pro.
It's
okay, thank you very much. So I'm sorry for the delay. So let me share my slide. Okay, now I'd like to begin. So thank you very much, everyone, including Sakurai Sensei. So I'm Kaoru Toko of University of Tsukuba. I'm so happy to have the opportunity to speak here. And today I'd like to introduce a unique method for the low temperature synthesis of group 4 semiconductor thin films. So this is the main background of our research. The coming super smart society consists of our real physical space and cyberspace, including huge database. Here, IoT collects any information in physical space, and then AI in cyberspace creates new values. So electric devices should be more familiar with humans and should be present in everywhere around us. Conventionally, most high-performance devices were restricted to single-crystal substrates with low versatility. So these functional devices should be developed to versatile substrates such as wall covering, transparent glass, and flexible plastics. So new technologies for thin film synthesis on these substrates are important. To achieve this, there are two challenges. First, the process temperature is limited to avoid damage to the substrate and the surrounding materials. Secondly, thin films fabricated on such amorphous substrates are generally of low quality. So I'd like to show a low temperature synthesis method called metal-induced layer exchange. So the layer exchange begins with annealing this structure. First, metal and amorphous semiconductor layers are prepared on a substrate. During annealing, semiconductor atoms diffuse into metal from the top semiconductor layer. When the concentration of semiconductor atoms in metal becomes saturated, nucleation occurs. After that, semiconductor atoms attach to the nuclei. This causes lateral growth. At the same time, metal is pushed up to upside because of the stress of the lateral growth. Consequently, a layer exchange is completed. So this layer exchange phenomenon was first reported in the aluminum silicon system by Australian group. We found that the layer exchange occurs in various combinations other than silicon aluminum system, such as germanium, silicon germanium, germanium tin, and carbon with some metals. Depending on the metal combinations, the resulting film shows various features, so various applications can be considered. Many applications have been proposed using layer exchange. Thin film solar cells are the most widely studied because layer exchange can provide large grains. Silicon, silicon germanium, and germanium layers formed by aluminum layer exchange can be used as a p-type seed layer to form a large grain light absorption layer. Germanium is also applicable to 3-5 compound semiconductors like this. This structure showed high photoresponsivity due to large grain gallium arsenide layer. In addition, thin film transistors on the plastic substrates were demonstrated using germanium formed by gold layer exchange. Good transistor operation was achieved because the solid solubility of gold in germanium is very low. Nanowire template is also an interesting application. Because germanium nanowires glow 111 direction, 111 related to germanium works as a seed layer that allows the vertical growth of nanowires. A thermoelectric device is one of the promising applications of layer exchange. Our target is the flexible silicon germanium thermoelectric device because silicon germanium is the oldest and most reliable thermoelectric material used in satellites. This graph shows power factor, a performance index of thermoelectric materials as a function of process temperature. In general, power factor of silicon germanium films decreases with decreasing the process temperature because the dopant activation requires high temperature. We overcome this problem using layer exchange because impurities such as aluminum and zinc can be self-organizingly activated. Silver is not a dopant for germanium, but by adding boron or arsenic in silver, p-type and n-type silicon germanium layers can be obtained. So layer exchange allows us to simultaneously achieve high thermoelectric performance and low process temperature. Layer exchange can also be applied to carbon materials. The 9 elements shown in blue cause the layer exchange between amorphous carbon. In particular, nickel allows us to synthesize graphite film and multi-layer graphene on insulators at quite low temperature. The quality is higher than most carbon film formed on insulating substrate. Graphite is used as the anode of batteries, so we investigated the anode application of the graphite thin film. This is the first demonstration of the anode operation of a carbon thin film synthesized at such a low temperature. So finally, I'd like to show future perspective of our work. Using the layer exchange techniques, we fabricated thin film devices such as solar cells, transistors, and thermoelectric generators, and batteries. So in the future, these devices could be integrated on a single plastic substrate. Of course, this is still a kind of dream, but I'm glad if it interests you. Thank you very much for your kind attention.
Thank you, the Professor Toko. And his the pioneered work on the low temperature the crystal growth is the hot topic for the integration of the semiconductor circuit on the plastic film. That is the one of the important point for reduction of the temperature to integrate the many material in the wide application. So now he endeavor about the new application the field. Therefore, after this discussion, if you have an interest, please contact him. Okay, thank you.
Thank you very much.
The final presentation from Tsukuba side will be given by the Professor Kazuhiro Marumoto. He is working on the organic electronics and the spin electronics. The Professor Marumoto, let's start your presentation.
Thank you for introduction. Can you hear my voice on screen?
Yes.
Okay. Thank you for Professor Sakurai for giving me chance to this opportunity to present my research, and also good afternoon, Baba California people, for your nice organization this seminar. I really thank for your every effort and contribution. So I'm Kazuhiro Marumoto, and the title of my presentation is a microscopic analysis of organic electronics using electron spin resonance. Okay, first I briefly introduce my lab at University of Tsukuba. So you know that Tsukuba is located at 55 kilometers from Tokyo, Japanese capital city. Here is statistics of the University of Tsukuba. And a total of 25 lab members is present at my lab. And here is a picture on the day of the graduation ceremony and the farewell parties. Okay, from this April, we established a new research center at the University of Tsukuba. I'm serving as director of this new research centers. It is an incubator for the formation of research center for the solution of global issues. And so we create a field based on the quantum spin science and technologies. So we use some future is we use quantum spins of electrons and nuclei as a probe to assess every factor such as properties, function, and performance for the organic semiconductors and inorganic semiconductor materials and devices and biomaterials and composite structure used in the airplane and automobile and geomaterials. Okay. So our research center is called Inorganic Quantum Spin Science and Technologies. It has a great potential in function and performance. So we we combine this disciplinary fusion of different fields such as microanalysis and theory and AI and material synthesis and macroanalysis and devices to create an innovation technology which can be used for the every field in the not only the science but also the application. So this center is open not only for the University of Tsukuba but also the worldwide people such as Baja California people. So if you're interested, please contact me to join, because we can provide many applications such as synthesis of materials and solar cells or lighting devices fabrication techniques. Okay, so here we show the organic electronics. This is a next generation electronics beyond the silicon-based and ionic-based materials. It is environmental friendly and low-cost application, and it has a most important point is a lightweight and flex structure right here. There is a typical devices such as organic transistor and organic perovskite solar cells and organic lighting diodes. Now each organic light diodes are commercial days, and they have a new application, next generation devices such as power generation in the world. In my lab, we do the research on the transistors and diodes and solar cells. Okay, so in my lab, our strength is our abilities to analyze electronic states inside operating devices in real time using the electron spin resonance technology. And here is the electron spin resonance principle. It is used unpaired electron under the applied magnetic fields. Under this applied magnetic fields, electron energy split right here, and we apply microwave to this system, so then it absorbs a microwave. So then we can analyze many microscopic properties using not only the sample but also the devices. The sample is inserted the captive resonators. We apply electromagnetic fields and microwave generator, and we detect absorption using these cavities. So here is the example of the transistor studies. So in organic transistors, no charge because it's a neutral materials, but by using the gas transistor structure, by applying voltage, the charge is injected in the semiconductor, so it has a charge, and not only the charge but also the spin. It has a first demonstration of the spin observation of charge carriers in organic transistors. So we, for example, we have analyzed wave function such as comparing with a monomer cation. So this extension of wave function demonstrates band-like transport even in the organic semiconductors. So here is another example of the thin film solar cells using the typical P-type semiconductor materials, polymer, and N-type semiconductor material fluorine derivatives. So under the device operations, so we have observed the light-induced signals, and each is demonstrates accumulation in this charge in the solar cells. And this accumulation shown by red circle is correlates decrease of the solar cells parameter of the short circuit current density. It is a mechanism of the degradation of solar cells. Here is another example of the perovskite solar cells. It is recently greatly developed, and it has almost compatible maximum efficiency to the silicon-based crystalline solar cells. So there are some advantages such as low cost and flexible and high efficiency, but disadvantage such as a degradation mechanism. So we now research find why this device degrades. So by this one example, by using this perovskite solar cell structure, and spirometers, it is a whole transport materials. So after our studies, we found in this materials, we found accumulation of the whole charge carrier, and this enhancement is created the decrease of the solar cell parameter of cyclic voltage here. So we can find the reason why this solar cell degrades. So, it is the last slide for the experiment. It is a new next generation light emitting electrochemical cells, light LECs. It has a very simple device structure as shown here. Only 2 electrodes is enough to light emit the light emitting material such as super yellows. So, but it has a problem of the degradation mechanism. So by studying the ESR signals, we can observe the charge doping in this device materials. So by analyzing these ESR signals, and we found the p-type doping and n-type doping progress under the device operation. So this is a operation mechanism we can find from this our results. So it's a summary of my talk, so we can evaluate the spin states and electronic application of organic materials and devices. So it is a collaboration between the wide range of experts with a series of new research. This is acknowledgement of my talks, and it's a collaborators from many researchers from not only the Japanese people, but also the abroad. And we work was supported by many funds shown here. Well, thank you very much for your kind attention.
Thank you, Professor Marumoto. And also before closing about the Tsukuba session on the semiconductor, I want to explain about the background of the organic electronics. So we have the Nobel laureates, and one is the Professor Hideki Shirakawa. He is the pioneer of the plastic electronics. He developed about how can we control the electroconductivity of the polymer material. And therefore, from that organic electronics field, like the Professor Marumoto suggested, that we have the many laboratories working on the organic type devices and the synthesizing about the materials. And the Professor Marumoto has a special technique of the characterization of the control of the electronics, like how the electron injection happen in the devices and so on. Therefore, he has the special skill of the low temperature growth organic or the organic inorganic hybrid devices. That is one of the hot topics all over the world. Professor Marumoto, thank you. And before closing, so I want to get the agreement for all speakers, the Professor Uedono, the Professor Toko, the Professor Okumura, and the Professor Marumoto. The Mexican side, the Baja California, the professor want to get your email address. Can we share about your email address to them? Okay, no problem.
Yeah.
Okay. Thank you. So after this session, I will provide about this email address to you. Thank you. And they will stay at this session for the final discussion that time. Okay. Thank you for your contribution. So I want to switch the chair role to the Professor Juan tells us. Okay. Let's start.
Thank you, Professor Sakurai. Good morning in Japan and good afternoon in Baja California. It's an honor for me to welcome you and introduce a distinguished group of researchers who will guide us through a series of fundamental topics regarding the present and future of the semiconductor industry. Mexico, and particularly Baja California, is playing an increasingly important role in this global industry. With its proximity with the United States, its growing industrial ecosystems, and the highly skilled talent from its universities, our region has the potential to be a key player in the semiconductor value chain. Now, more than ever, it's essential that we continue investing in research, development, and talent for this field to seize the opportunities and face the challenge that the future presents. In this seminar, we are honored to have the participation of 5 distinguished researchers from universities of Baja California, who will share their knowledge and experience in key areas related to semiconductors. They will help us to better understand how emerging technologies, new manufacturing processes, and innovative research approaches are shaping the direction of this dynamic industry. Let me briefly introduce our first speaker for today, Dr. Nicola Ratnedev from UABC. He will present us the topic metal oxide semiconductors for application in transparent flexible devices. So Dr. Nicola, please, the floor is yours. Welcome.
Thank you. Thank you very much, Juan. Good morning and good afternoon, everyone. The topic of my presentation is, Juan, can you hear me?
Yes, perfect.
Yes, and the presentation is also seen.
Yeah, you need to click
Okay,
on...
yes,
yeah.
I'll do it. Yes.
Yeah.
Yes?
Yes, it's perfect. Yep.
Thank you. So the topic of my presentation is metal oxide semiconductors for application in transparent flexible devices. And this research has been carried out at the Institute of Engineering at the Autonomous University of Baja California. This is the outline of the presentation. First, I'll talk about zinc oxide, which is an N-type semiconductor. Then I'll talk about nickel oxide, which is an P-type semiconductor. Then I'll briefly discuss aluminum oxide, which is an insulator. But to fabricate thin film transistors, we need a material for gate insulator. And then 2 applications with these materials that we study. The first application is in thin film transistors, which are based on zinc oxide, aluminum oxide structure. And the other presentation is the other application is in broadband photodetectors based on heterojunction diode, P-type nickel oxide, N-type silicon. So the layers of zinc oxide that we studied were deposited by plasma-enhanced atomic layer deposition at low temperature, 70 degrees Celsius, because they are oriented for deposition of flexible substrates. As precursor, we use diethyl zinc, and as oxidant, we use 2 types of plasma, water vapor plasma and oxygen plasma. And the growth rate per cycles are given here, and they are slightly higher for water vapor plasma, and the band gap of the materials is almost the same, 3.2 EVs. X-ray photoelectron spectroscopy indicated that the layers are carbon-free with high purity. Another observation was that the layers deposited with water plasma have higher concentration of oxygen vacancies. And since these vacancies are related to the precarrier concentrations, it should be expected that they have lower resistivity. And this was confirmed by current voltage measurements on layers deposited on quartz substrate. As it can be seen, the water vapor plasma leads to layers with much higher conductivity. The materials are with nanocrystallites, which are oriented along the A and C axis, and the size of the crystallites depends on the substrate, but varies between 12 and 18 nanometers. The films are smooth Of course, the surface roughness depends on the substrate. These excellent surfaces were obtained on polished crystalline substrate. However, when the film is deposited on ETO PET substrate, the roughness increases almost 10 times. The result that we obtained, optical, morphological, structure, compositional, showed us that these films are promising for flexible electronics applications. The other type of semiconductor that we studied was nickel oxide. 3 types of nickel oxide were studied, obtained by RF magnetron sputtering and by thermal oxidation of evaporated nickel, so metallic nickel. So the sputtered layers were obtained with RF power varied in this range and in temperature range between 25 and 100 degrees Celsius. And we used as a target nickel oxide. The layers obtained by oxidation, thermal oxidation, were of E-beam evaporated or thermally evaporated nickel. One important result was that the sputtered layers are superior in regard to the concentration of bulk defects. Very low bulk defect densities, very low defect densities at the nickel oxide silicon interface, and higher degradation voltage. Also, another observation was that the effect of RF power and of deposition temperature is the same. It's quite similar. Both lead to an increase of the layer resistivity. Aluminum oxide was deposited also at low temperature, 70 degrees Celsius. As precursor, we used trimethyl aluminum, and the same oxidants have been used. Some of the main characteristics of the deposited layers were high transparency, high purity carbon-free layers, very smaller concentration of hydroxyl groups were found in layers using water vapor plasma. The band gap of the materials was about 6.6 EVs, and the films were smooth and with a dielectric constant of 8. One important difference is the breakdown voltage. The layers deposited with water vapor plasma show much higher breakdown voltage compared to the layers obtained by oxygen oxidant. Here we have the thin film transistor fabricated on glass substrate. This is downgate configuration. We have a thin aluminum layer, aluminum oxide layer deposited at 70 degrees Celsius with a thickness of 25 nanometers, and we have a semiconductor with 60 nanometers. So this is an optical image of the device, and we studied transistors with channel length in this region, and the width of the transistor was kept constant, always 40 micrometers. Some time images show that the layers are uniform and with a smooth interface. The electrical characterization show that the transistors have good properties. Very low leakage current was observed, 10 to the minus 13 amperes. The breakdown voltage of these films, which were deposited with water vapor plasma, is very similar to the one that we have seen on silicon substrate, 5.6 megawatts per centimeter. The threshold voltage of the device is also very good. The mobility is a parameter that has to be optimized, and very good on-off ratio. The subthreshold swing was in the range between 190 and 207 millimeters per decade, depending on the channel length. The other application was in broadband photodetectors based on this on the heterojunction diet using nickel oxide and N-type silicon. All three type of devices with nickel oxide layer deposited at the different powers showed good photoresponsivity. However, I would like to mention that the layers deposited at 60 watts showed higher short circuit current, which led to higher responsivity at zero bias voltage. So these results about this device in self-power mode are among the highest results reported in the literature for nickel oxide-based photo detectors. And we have some other projects, but because my time is over, these are developed in collaboration with the School of Engineering, Institute of Engineering, and some other university. Thank you, universities. Thank you very much for your attention.
Thank you very much, Dr. Nicola, about your presentation. This is a point of interest for both universities, not only Baja, but also Tsukuba. So this could be a good point of start for discussion after we finish the presentations. Thank you. Following with the presentations from Baja California, I'm honored to present Professor Amanda Nieto from CETIS. She will present us the synthesis and characterization of indium gallium nitride nanorods for gas sensor applications. So, Professor Amanda, thank you for being here, and you can start.
Thank you for your presentation, Dr. Terrazas, and thank you everyone for having me this afternoon. Good morning to everyone in Japan. Could you confirm if you can see my screen?
Yes, we can.
Thank you very much. Well, as Professor Terrazas mentioned, my name is Amanda Nieto, and I'm currently working at CETIS University in Mexico. Today, I will talk a little bit about previous work that we have developed based on the synthesis and characterization of indium nanorods or indium gallium nitride nanorods for gas sensor applications. So I will give a brief resume of what we did. So what are these? Why are those materials of our interest? We all know that nitrides belonging to the third group can be used in optoelectronic systems. And if we can manufacture them in a way that we can choose the energy gap which they can work with, we can develop materials that are smart for specific purposes. Specifically, indium, aluminum, and gallium nitride are alloys with band gaps which range from 0.7 electron volts to 6.2 electron volts. So developing different ways to synthesize them in order to tune in this specifically band gap can offer an alternative to produce semiconductors that will serve to specific purposes. Specifically, the compound of indium gallium nitride results very attractive because it can be tunable to these characteristics. They are compatible since they have a Wurtzite crystal structure and they both have a direct band gap energy structure. However, the difficulty in growing this system of gallium nitride stems from several factors. Some of those are that there is a large difference in interatomic spacings between the gallium and indium nitride lattice, and as well as the high vapor pressure of the nitrogen indium, which can be tricky when we are using a thermal procedure to synthesize it. So you should be very careful with the temperature that you are working with. So regardless these issues, we propose a hypothesis that the one-dimensional nanostructure growth will allow us to grow gallium indium nitride crystals with a high content of indium in their structure. Why do we want to tune the indium content? Because, as I mentioned before, we are interested in obtain a specific band gap for the electronical purpose that we are pursuing, in this case, gas sensors. So our general objective was to grow a semiconductor nanowire of gallium indium nitride using the CVD method combined with a BLS procedure with a high concentration of indium. So the methodology that we worked was divided in 5 stages. First of all, we use coarse substrates that were cleaned in the previous step. After that, there was an evaporation of a gold film on the coarse surface. There was a thermal treatment to form gold nanoparticles on the substrate. And after our substrates were ready, we used a CVD process for the formation of ingot nanowires. And afterwards, we proceed with the characterization of the obtained samples. So once the substrates were ready, we proceed with the CVD, which is a chemical vapor deposition process for the formation of gallium indium nitride nanowires. The process is very standard. We start with a coarse tubular furnace in which we introduce a coarse substrate with the previously formed golden nanoparticles. After that, inside the tubular furnace, we introduce a coarse crucible containing the amount of the metals that we will be using. Later, I will show you the different concentrations, which can be indium and or gallium, depending on the sample. The CVD reactor was injected with a flow of ammonia at a rate of 120 milliliters per minute. Then the temperature of the reactor was gradually raised to 750 degrees, and we kept that same temperature in the system for 30 minutes with a constant flow of ammonia. After 30 minutes, the flow of ammonia was stopped and the furnace was allowed to cool down. And once the system was cooled down, we take the samples in order to perform further analysis. So what we were aiming with this procedure was to achieve a BLS process with a combination of chemical vapor deposition. BLS process stands for vapor liquid solid process, in which we start with the gold film over the substrate, the coarse substrate, which had a thermal treatment or promote the coalescence of this metal catalyst to form gold nanoparticles, which once they were inside the tubular furnace, were saturated with the precursors, the metallic precursors, and the gas that was acting as a precursor of nitrogen and also as a carrier gas inside the reactor. And the material tends to get inside the gold nanoparticles, and once the gold nanoparticles are separated, they tend to precipitate. After they precipitate, they start to grow in a one-dimensional structure, which it was what we were aiming for. Some of the results for the characterization were, first of all, we have to characterize the gold nanoparticle size in order to be sure that they were behaving in the way that we were expecting. We proceed to vary the content of gallium in nitride-indium nanorods that were at the beginning 100% pure, and then we start to add in a little to change the quantities of gallium in the concentration. So we name these samples A, B, C, D, and I will be referring to this later. After the CVD process, we start with scanning electron microscopy images in order to ensure that we were obtaining these nanorods. We were very interested in the one-dimensional structure, so we need to be sure that we were obtaining that. And as we can see, these are the samples that I was referring before with different gallium contents and different indium contents in the nitrides. We start to see that the gold nanoparticles, some of those start to coalesce between them and they create bigger nanoparticles, but most of them start to grow these materials in a rod way. Different thicknesses, different lengths, but most of them reproduce the BLS process that we were aiming for. So we start to look out at what were the difference in the morphology as the gallium content increased. We performed a transmission electron microscopy on the samples in order to see if the mechanism prevails. And we found these particular structures inside the rods that were present in all the samples. These particular elongated formations can be seen that they're on the same position inside the rod, and they maintain the same crystallographic orientation as the rest of the rod. When we performed the high-resolution TEM images, we found that the growing direction for the rods were the 0001 planes, and they had an average lattice parameter of 4.16 angstroms in some of the samples. We performed this analysis on two samples, sample A and sample F. And we found the same structures inside the wires. And for the sample F, which was the one with higher gallium content, we found a lattice parameter of 3.9 angstroms, which it is a intermediate lattice parameter between gallium nitride and indium nitride, which is 4.16 angstroms. After that, we performed the crystallographic analysis, and we identify the main diffraction peaks. We see that all the samples were growing along, preferentially along the 1010 crystallographic plane, remembering that this is an hexagonal structure. But we can observe a small shifting of the main crystallographic plane towards greater angles. So we can see that since our samples are shifting to greater angles, this will be, or this could imply a shrinking of the lattice parameter. So this could be associated to the insertion of bigger atoms, which are the indium atoms in the crystal lattice of the gallium nitride, which was corroborated by the TEM analysis. And finally, we performed catoluminescence analysis, and we see very clear that there was a shifting in the band gap of the samples. We start with the 100% indium nitride, and then we start adding gallium to the volume, and we see a considerable shifting on the band gap energy to our final value of 2.75 electron volts at the higher content of indium. So we can see that the structure is being modified by the experimental parameters in a way that we were expecting. We can confirm from TEM analysis and from crystallographic analysis that there are a shrink in the crystallographic cell, which implies that there has been a good adoption of the system. So we can perform this process in order to obtain rods with a specific energy band gap that could be used in optoelectronic devices as well. So in conclusion, the CVD method shows to be a possible way to achieve unidimensional growth of ingot rods with a high indium content in its structure. These resulting rods exhibit good crystalline quality, luminance emission, and diameters which are not exceeded 60 nanometers. And we have a good opportunity to develop rods that can be designed with a specific and adjustable band gap tailored to technological needs. So that will be all for my part. Thank you so much for your attention.
Thank you, Professor Amanda Nieto. Yeah, it's evident that nanorods play a crucial role in the development of new materials and new semiconductor devices. And well, this is an example of an application for gas sensors. Thank you for your contribution.
Thank you.
I want to present now Professor Enrique González Aragon from UTT. He will present quality standards and talent development on manufacturing. Professor González, the floor is yours.
Hi, everyone. This is Enrique González Aragon from UTT. Let me share my screen. Would you let me know if you're seeing my screen?
Yeah, yep. It's not in
Okay.
a slideshow. It's not yet in slideshow mode.
Okay, let me put it.
Here you are. You're
Okay,
ready.
thank you very much. Okay, my name is Enrique González Aragon from UTT, Technology University of Tijuana. I'm presenting what we are doing here in the university. Let me just tell you, we're just diving into the semiconductor. We don't have so much investigation yet, but here's my presentation. This is the agenda. I'll talk about the semiconductor industry in Mexico, actually Baja California, the skill talent requirements we need, the academia role, the quality standards for the UTT participation. Okay, this is nearshoring opportunities in Mexico. It's like the roadmap for the bringing the semiconductor industry to Baja California. So first of all, there are several key areas we need to focus, like the supply chain, the infrastructure, the workforce, the entrepreneurship, and innovation. So how do we kick in here? Well, we'll have a workforce where we can develop the skills that the students need to work in the semiconductor industry. This is a map of our Mexico. This is a supply chain segment, no? And we are located here in Baja California at the red square, top left. You can see a red dot square. There's where we are located. Among all sites in Mexico, here we have with dark blue, clean room networks, design, manufacturing, ATP, R&D, and how are distributed along the country. Here in Baja California, we have only 3 of those, which are the clean room network, the ATP, and R&D. Okay. Regarding talent needs in Mexico for semiconductor, well, the objective is to identify and develop the core competencies as well as specialized competencies tailored to meet the semiconductor industry needs. So we need to develop some students that will know some of these skills, like design engineers that design the process, design testing, etc. Also, as well as assembly and test engineers to oversee the process, and assembly and test technicians for machinery setup, test runs, etc. Quality engineers to assure that the final product meets the quality standards, international standards, and of course, software engineers that support on the data analytics and many other things, okay? So we have a triple helix here in 3 major players that working together to bring the semiconductor industry in Baja. We have the government side, we have academia, and we have industry. In government, we have the Ministry of Economy. In industry, there are already 3 companies in Baja, which are Qualcomm, Infineon, and Skyworks. On the academia side, we're working with the Arizona State University, Tech Institute, and of course, some of the Baja California universities like UTT, Baja California Autonomous University, CETIS University, among others. And now talking about UTT, which stands for Tijuana University of Technology. The model here is 70% practice, 30% theory, and we have 3 internships. We go for quarters, not semesters. And the first 6 quarters, the student get a degree for as technician, we call TSU, standing for Technical Superior University. And after that, at the 6th quarter, he goes into an internship, and as well as the other. After he finish, he has option to choose as a professional license or engineering. Professional license, it's another 3 quarters, engineering and another 5 quarters. And at the end of each one, like the 9th quarter for professional license and 11th quarter for engineering, there's another internship where the student goes to the company, to a company, develop a project, solve a problem, and write their memories like a thesis. So he graduates with that. And the university focuses mainly in engineering. Of course, we have a commerce, import-export, accounting, but mainly engineering like mechatronics, electromechanical engineering, etc. And we have also the process and industrial operations engineering. Here is where the quality fits in, because we have 3 degrees actually, one in quality, one in manufacturing, and one in molding. And the model is 70% practice, 30% theory. And graduation profile of the student, and the process and industrial operations engineering, he will be skilled on making production master plan in order to meet the quality and customer requirements based on international standards. He will be able to manage the quality management system, making process standardization, quality manuals, and developing engineering systems that meet the quality standards, ergonomics, and health and safety. And of course, they also get some certifications. And at TSU level, they get the production line balancing certification, and in engineering, they get the 2 quality tools, lean manufacturing and Six Sigma. And regarding the UTT participation in the semiconductor industry, we're involved in the training program. As you know, there's a training program. And the objective is to generate skilled manpower to supply the emerging semiconductor industry in Mexico. We already have 13 professors participating on the training program. We have the relationship with the academia, government, and industry. And in future, we're planning to open a new degree in semiconductor at UTT, possible 2025, next year. And as a conclusion, we're looking forward to participate in this new opportunity in the semiconductor industry. That's all for myself. Thanks for your attention.
Thank you, Professor Gonzalez. Talent development is clear that will help us to continuous learning, upskilling, and lean manufacturing, and will help reduce costs for the companies that are located in Baja. So this is a great effort from academia, government, and other institutions to continue the development of talent in our country. Thank you very much.
Thank you.
Let's continue with the presentations. I'm honored now to present Professor Roberto Carmona Rodriguez from the Ibero-American University, Ibero. He will present on impedance control and force sensor design. So, Professor Carmona, the floor is yours. Thank you. You are on mute, Professor Carmona.
Now, yes, that's right. Yeah. Okay, so my name is Roberto Carmona. I'm with the Ibero University, and those are my contact number and my email. If anyone wants to send me a message or contact with me, feel free to make it. So today I will speak about the neural PID admittance control for robots and for sensor design. Okay, so this is the content of the presentation. In this work, there are two main investigations that motivate this research project. The first one is the paper carried by Joe Perry and Jacob Rosen. In this paper, related with the beam power exoskeleton design, they propose exoskeleton as a cinematic chain, and they describe the force of the exoskeleton by the force applied at the shoulder, the force applied in the elbow, and the force applied in the wrist. So they use with these three sensor force, they describe perfectly the kinematic model and dynamic model for the exoskeleton. So they'll explain how to pull it, the train can increase the upper limb force detected by the force sensor in the 7 degrees of period exoskeleton. So it's very interesting. So how they describe perfectly the cinematic chain in the mathematical model. So we use this model in the second one to study the first one, a PID tuning method for control. In this PID tuning method for control, we collaborate with Jacob Rosen, but at the first one, we use the model to describe in a mathematical model. So we apply the Euler-Lagrange equation in order to propose a stable PID controller. Or stable PID controllers is composed of several PID controllers, and the first one we propose the nonlinear PID nonlinear system. We propose a linear system controlled by the all force control. So after we propose analysis stability, and we prove by a Lyapunov function that the system in closed loop is totally stable. In each joint, we propose the second order system in order to choose the control gains for the all PID control. So after we compute some simulation and propose how to prove to validate in the 7 degrees of freedom rule. The third one is a neural PID admittance control for robot. We make this part of my dissertation PhD degree, in which one the admittance control basically is the input force is the controller output motion. That means in the right hand we have the exoskeleton modeled by this system, and we choose the classical linear PID control compensated by a neural compensator. So in order to approximate the KPD, KPE, and K gains by the artificial neural network. So we propose in the exoskeleton for the 7 degrees of freedom the same Euler-Lagrange equation, and then we propose the control law. The control law, as we can see in the right hand, is the PID control plus the neural compensator. So we can choose we can choose this control law. In this work, we describe perfectly the methodology, but in this resume, I just told you that the neural network is composed by this hidden layer. We prove with different artificial neural network, but with a simple perceptron layer, we can approximate perfectly the gain. So we prove the convergence of the error as in the last work, and now the impedance control for robots. Basically, is the same methodology, but in this case, we propose the same non-linear system based in the Euler-Lagrange equation, but now we express in matrix form. This matrix form, we can see that it's a linear form and it's easy to analyze. So we propose a neural compensator like the other one. So in this case, the difference is that the input is the portion or velocity, and the control generates the force. That means we have the output of the skeleton, and we feed the controller with the position or velocity of the algorithm, the impedance algorithm. So it's relatively easily to prove that the stability is converged to zero. We propose this theorem in the study, and the object of this theorem is show that with the structure of the kinematic model, we can choose with the boundary condition the gains for KE, KP, KD. The gains will be more easy compared with other methods, choosing with all artificial neural networks. So we validate this work in the 7 degree of freedom exoskeleton, and we obtain this matrix gains, and after we prove in each joint. So in this presentation, I only put two joint, but in the full work we can see the totally joint. So the next step is we want to construct a kind of exoskeleton in the diversity, but we need some different sensors. So the first step is construct a resistive sensor. In other hand, develop a sensor forcer for distinct prostheses, and in order to measure the deflection in the wrists and fingers, and finally measure the deflection in the flexi robot that is another kind of robot. So there are different works in the biography. We choose this paper. This is a review paper, and we can consult. That is important for us because in this paper tell us how to make measure the deflection in wrists and fingers. So the second one, basically a variable a flex sensor is a variable resistor in which in position normal there are no change in resistance, but if we put any force to the resistor, the resistor will be variable in time. So how we want to make this flex sensor? We want using additive manufacturing. There are a lot of studies about the additive manufacturing, but I chose in this presentation, this review. But in this review, in fact, they tell us that the flex sensor will be basically will be by a constructed ink, a phenomic resin layer, and the segmented conductor. So actually, we want to are part of the BEC Semiconductor Talent Development Program, as tell us the last panelist. And we are studying the process to apply the methodology for impedance control processes. And we are considering buy a material printer. And finally, in order to carry a research project with the Physics Institute of the UAP Mexico. So that's my presentation. Is anyone have a view, please feel to contact me. Thanks a lot. Have a good time. Arigato. Thank you.
Thank you, Professor Carmona, for your work. It's evident that robotics and new materials can enhance the control of these kind of systems and also interact better with humans. So
yeah, that's right.
A very good line of research. Thank you.
Thank you for it. I appreciate it.
Thank you. And finally, for this block of presentations, we have Professor Miguel Alejandro Muñoz Lopez from the educational group 16th of September, that he will present techniques for recycling electronic components in screens liquid crystal. So Professor Munoz, the floor is yours. Is he present already?
Yes, hi. Good morning, Japan. Good afternoon, Baja. My name is Miguel Alejandro Munoz. I am part of the GETI Mexico High School Federal System, and I am also collaborating with Grupo Educativo 16 de Septiembre. Let me share the screen. Can you please confirm if you can see the screen?
Yes, we can see it, but it's not in slideshow mode yet. Okay.
Okay, thank you very much. This research is about recycling electronic components in liquid crystal screens. I'm going to try to make an easy explanation because this is a very technical stuff. So let me start with this information. Okay, if you have the flat TV, you have the HD TV, maybe you got with the juice, you got the broken TV. And what I talk about, maybe you got some lines on your screen, maybe you see dark sections on your screen, maybe half the screen is not working on your flat TV. Well, let me tell you something. Much probably is because this little body right here, this small chip is not working. Well, in high definition television, the components called tap drivers are an essential part of the operation for a liquid crystal display, LCD. What is the main function? The main function for this component is to feed the video signal generated on the HDTV electronic cards directly to the LCD and acting as an interface between the card and the glass section. I mean, all the signals processed on the electronic cards, the top driver helps to see on the screen on the LCD. Mainly, we have two kinds of top drivers. One of them is the chip on flex, and the other one is the chip on glass. Okay, the chip on glass, it means that the top driver is above the LCD screen. And the chip on flex, it means that the top driver is together with a kind of flexi cable, a flexi printed circuit. Okay, this is mainly what is a top driver. Okay, let's make a deeper focus on the top driver. If you see right here, you have the flat TV. Let's put our eyes on the screen and right in the corner. What is inside this corner on the LCD? Okay, what we see is the liquid crystal display, the top driver, and the PCB. Okay, let's make it even deeper in this section. What are we going to see? We're going to see part of the LCD, the top driver, flexi cable, another section of PCB, and this yellow section is an isotropic conducting film, which is kind of an adhesive for the top driver. Okay, the top driver is encapsulated on a flexible plastic film or substrate with conducting material interconnection at each end. The material connected directly to the LCD and PCB with the desit along its edges. A desit is made from micro gold spheres that upon contact with the substrate and the flexible substrate and applying contact heat, that driver then is placed. This is a complex process. This an anisotropic conductive film. It has the gold microsphere that once that you apply heat with a complex process, as I said, it can be placed and then it's going to interface the signals to the LCD. And after that, we can see anything on the screen. Okay, let's talk about the recycling methodology. Okay, you got the broken TV, the broken flat TV. Well, I have bad news and good news for you. Well, let's start with the good news. The good news is that the flat TV can be repaired. Okay, we have the solution. The bad news, it has to be repaired by a professional lab. I mean, we cannot take the flat TV and take it to the regional, normal electronic lab because the complex is a little bit difficult. Well, how can you do in this process on the lab, on a professional lab? Well, we have right here, what we see is an LCD screen for this section. This is the PCB section, and right here, this brown parts right here inside is the dot driver. Okay, if we would like to repair one flat TV and take the part for another broken flat TV, we need to remove it. But it's not so. It's not easy because if we apply a lot of heat, we can damage the dot driver. Even if we apply very low temperature, I mean maybe 40 Celsius degree, maybe we can remove it. But if we don't make the right process, we're going to damage the dot driver. Okay, the technical process is to put a resistor, which we're going to activate by the electric voltage, and we're going to connect it to a flat surface, a middle flat surface. And then we're going to place it just right here on the LCD. What do we have about process on this section? We have conduction heat transfer, and then we have convection heat transfers, because remember that the LCD screen has liquid inside. So this is what it makes more difficult, that we have solid surface and that we have liquid surface. And in that way, the heat has to reach the top driver, and the temperature needs to be enough, but if it is too much, it's going to damage the top driver. So the process is complex, but it's not impossible. Okay. Right here we have some information about what is happening on Latin American countries, talking about the electronic waste. We see from 2014 to 2018, right here, Brazil, Mexico, what numbers they're generating on electronic waste. So right now, of course, we have more waste at this 2024, but we have some process that we can help to reduce that electronic waste. This is one of them. And for the last, let me tell you that this research was made a few years ago, but in that time, semiconductors were not so popular right here on Baja, but right now they are. So this is why we are taking back this process and show it. Thank you very much.
Thank you, Professor, for your presentation. As we continue growing in technology, we are prone to create more electronic waste. So it's an important concern for all countries that want to maintain sustainability with the environment. So thank you for your contribution. And well, this is the last presentation from Baja's California University. So we are now ready to start discussion about possible areas of interest between researchers of University of Tsukuba and researchers from Baja California. Just to start the conversation, maybe we can start maybe the discussion about flexible devices and other applications for the Semiconductor Center that University of Tsukuba already pointed out during the presentation. So I don't know who wants to start the contribution or the discussion about areas of interest that we can start doing joint collaboration and research.
So I want to mention about some of the gratitude to all of the presenter, since we can catch the many information for some of the seed for the industrial application and the scientific application for both sides. And today, we can, our side, we prepare about the presenter for mainly the focus on the material and the device fabrication for the fundamental stage, but also we are connected to the application side. So this is our point, and the professor Ueno knows so well about some of the broad picture of the semiconductor, not only for the science, but for some of the application. Therefore, if you can, your side, you have some of the interest, that we can continue about some of the conversation. And as for the robotics application, we are so sorry, so we cannot prepare about the presenter about it. That since all four presenter is belong to the Institute of the Pure and Applied Sciences. And as for the robotics area, this is the information and the system, the engineering field. Therefore, we have another presenter on this point. But the latter session, we can have some of the presentation or the automatic, the vehicle, the operation, and so on. He is the one of the professor working on this field. Okay, this is our distribution. Thank you.
Yeah, thank you. Thank you. Yeah, I concur on the assessment. The starting point was semiconductors and materials, but as you can see in the presentations, there are many applications of this, even though flexible electronics are also artificial intelligence, telecommunications, and in the last presentations about robotics. So we can also continue the conversation about those topics and the applications of semiconductor in many fields.
Yeah, this is my opinion. For starting about some of the conversation and the collaboration, the student mobility is important issue. Therefore, if the Baja California government or some of the members support about some of the travel fee or some of the fee for coming to Japan, we are welcome to accept about these students as the educator about this type of the topic. And in particularly for the Professor Okumura's case, he has the many method for the fabrication of the gallium oxide-based devices. This is novel technique. Therefore, that can provide about some of the knowledge to the Mexican side of this wide gap semiconductor application. But also, of course, we can join about some of the team working on the nano, the 3-5 material also. Therefore, from the encouragement of the communication, firstly, the contact is important. But the next step is the student mobility. This is what we think about the future direction for the communication.
Sure.
How do you think about the Professor Marumoto?
Yeah. Can you hear me?
Yeah.
Yeah. Of course, we are happy to accept Mexican students. So if you have interest, so we are open for welcome. Because so now it is a very important time to develop the collaboration over words. So it is no problem. So we are ready, Professor, because Professor Sakurai very have a great efforts contribution to the develop the collaboration between other countries. So if you have, of course, short time stays also welcome. 1 week or 2 weeks or 3 weeks. So Japan is a neighbor country to the Mexico. So it is very easy to come to Japan. So of course we can go the Mexico. So I have not been in Mexico. So if I have a chance, I want to visit Mexico. So okay. So Professor Sakurai, do you have some fund or support for the traveling students from the Mexico, for example, the short stay?
Okay, so I want to explain the one of the idea that to utilize about the Sakura Science program. Okay, I want to share about the information.
Sakura's, okay,
Yeah,
please.
this one. This one is the Sakura Science program that provided by the Japanese the organization on the Science and Technology Agency, and this the program is the maximum is the 1 to 3 weeks, and the maximum number of the exchange is the 8 students, including about the faculty member. So I suppose this is the one of the important process to make some of the conversation for the field. And this program, the cover, as for the program type A, open application program, course A, that is this year the have already the finished, but next year we can apply some of the courses. For example, the late May to the March 14, this is this year's information, but the next year's one. And this start from the next January. And in that case, if the result is up, the announcement is the April, July, and November, then the US student can come to Japan as some of the internship or the watching about the laboratory. It depends on the program. And that start from the May, August, or December. Therefore, this is one of the starting point for the conversation. And the important point is the faculty member can join as a accompanying person. But in that case, we have to reduce about number of the visitor. But here, this cover about the travel fee and the residential fee. Therefore, it is one of the good program to know each other on the Tsukuba. Okay. This is the one of the idea, but also that we can have another scholarship system or the student the educational system. Therefore, this is another option. But as for the initial term, that we can utilize about this type of the funding source. Okay, this is what we want to share about the information. Okay.
It's a very good program. I think this can be beneficial for students pursuing a master or a PhD, and also faculty who wants to get trained in new technologies. So I think this is a very good information that we can share with all the universities. Thank you for sharing this opportunity.
Yeah, we need to keep about some of the targeting the age. So if the Mexican student want to join about the master or the graduate school, of course the final year that is the senior the undergraduate, or the master course the first year student is the one of the promising target.
Okay.
But also of course this is the short term. Therefore, if you want to encourage about the PhD course student to get about knowledge, that is also welcome. But I suppose for the future perspective of the collaboration, such kind of the funding scheme is important to make a strategy. How can we build about collaboration?
Thanks so much.
Thank you.
And Professor Okumura, do you have any opinion about some of the collaboration or the student mobility?
So we are happy to receive the student, but in my laboratory is no PhD and postdoc, so maybe go to Mexico is hard. Yeah, but I'm glad to receive student. And collaboration also. I'm very happy.
Yeah. And the Professor Okumura has many network with the US and European community, therefore, on the wide gap semiconductor. Therefore, of course, if the student join about the Okumura laboratory, and they can get about the important technique for the discover about the new field of the collaboration. Of course, in that case, our Japanese governmental funding is one of the source, but also if the Mexican governmental supporting the system or some of the scholarship that will be held, then it might be effective, I suppose.
Yes, for sure. Dr. Nicola, any thoughts about possible lines of collaboration from your perspective?
Thank you very much, Juan. I was very interested, and I have a specific question for Professor Tocco. What he told us about these flexible devices and these materials, as far as I understood, these are amorphous materials, and starting from these amorphous materials, by this technique, they want to improve their semiconductor properties. And this reminds me very much about the amorphous silicon. The amorphous silicon and metal-induced crystallization. So I think this is very interesting, and this could be an area of collaboration, because we are interested in transparent devices, and of course we are looking also of transparent and flexible devices. So maybe the experience with these four group materials could be useful in some regard. So I find very good opportunity for collaboration, especially for these materials. Of course, for us, will be very useful if we could use some of the analytical techniques that exist, that are developed in Tsukuba University. So I consider this could be very good opportunity for us. We are very grateful. Thank you very much for your time, for sharing the information, for sharing this scholarship internship programs. So this could be very useful. Thank you very much.
Yeah, thank you. So of course you can contact the Professor Toko Sensei since he is much focused on the flexible electronics,
Yes.
in
Yes,
particular for the control the crystallinity, and also this is that we can see today the topic on the flexible electronics. Therefore, that may be fit. Okay.
Yes.
So
Thank you. Thank you very much. Yes.
time is a little bit limited. Therefore, Professor Uedono, do you have any remarks?
Well, not really.
That
is all. That is your yes, Professor Sakurai's comment is all.
Yeah. And anyway, the Professor Uedono has the many options for the collaboration, the cooperation, and he has a special technique for the defect characterization using the positron. This is a special one. Therefore, this is the good source for some of the conversation. Okay, so sorry, the time is a little bit limited. Therefore, we start about the break for this session, and then the start about the AI session after the 3 minutes later. Okay, for all presented, thank you for your contribution for this nice session. Thank you.
Thank you very much.
Thank you so much.
Invitation. Thank you. Thank you very much.
Thank you. Time.
Thank you, everybody, for your valuable information, investigations and research that our panelists have shared with us today regarding the semiconductors industry. As it was mentioned before, we're going to have a couple of minutes for a break, and we're going to be back for the next segment of our seminar.
Thank you. We'll be back.
Welcome back, everybody. We're gonna continue now with the second segment, which is gonna be artificial intelligence. This segment will be moderated by Takeaki Sakurai from Tsukuba University and Professor Andres Ibarra Lafarga from the Technological University of Tijuana.
Okay, thank you. Welcome back. And today, I wanted to have the second session, the focus on the AI, automatic driving, machine learning, and the quantum information. And the Mexican side, the healthy aging, the robot, and the space, the mining robot. This is an interesting topic. Then we can have some of the exchange of the information and the future collaboration. So let's start about the first speaker, the Professor Tetsuya Sakurai. He is working at the AI Science Center. Okay. 桜井先生は、OK。 See. Okay, wait a moment. Indeed. He is in the list of the attendee, not the panelists. Therefore, we cannot see about it. The professor he is joining about this session. Okay, this is the system one. Therefore, would you solve about this issue? We can see about the presenter Tetsuya Sakurai and the Professor Makoto Ito, Professor the Nova Anna, they are joining about the attendee list. Therefore, if they switch to the panelists, then they can have that presentation, I suppose. Yeah. Firstly, I wanted a little bit the switch about the presentation since the Professor Makoto Ito is the next schedule at the 15. Therefore, 伊藤先生、最初にプレゼンテーションお願いできますでしょうか。
はい、大丈夫です。So, can I share my screen?
Okay. He is working on the automatic the driving, and then move to the Professor Tetsuya Sakurai. Okay.
Okay, so can you see my screen?
Yes.
Okay, thank you. Thank you, Professor Sakurai, for your introduction. My name is Makoto Ito. Today, I would like to talk a bit about our research on automated driving. Let me start from the basic the philosophy of our research. We are interested in the human-machine interaction. And basically, we do some research on understanding of the human nature of the cognition and the decision making. And based on that, we design the system of the human-machine interaction. The application domain is advanced driving assistance systems or automated driving. Or we do a little about the drone or air traffic and train or some other transport domain. But mainly we are doing the automobile issues. So we are doing the research on automation, but the automation does not mean to remove the human. Even though the level of automation increases, still the human should be in the loop. So the question, for example, in the automobile domain, some people say that I want to drive, even though the automated technology is available. So the question here is we have the basic philosophy of the human-centered automation, in which the automation should be designed for the human operators to be in command, to bear the responsibility to attain the safety. That is the basic philosophy of us. So the question is, how can we assist the human's activity, driving, for example, with the automation or AI technologies? So that is the very important question for us. So we have this kind of the framework that the human and AI automation makes a team and interact to solve a problem or to do some task. So here today, I would like to focus on here the decision-making process of during the driving. In one of the decision-making of the driving is to choose the speed. So I will a little bit speak about the how to recommend the speed during the drive. Then let me show one video of the near miss of in an urban area of the Japan. This is a taxi near miss case. So as you see, even though the driver is driving safely, but still the risky situation may happen. And in some cases, they attain the safety, but in some cases they not. So the question here is how we can reduce the risk. Sorry. So we would like to obtain the better speed. I mean, the not too risky, but not too slow. Of course, if you reduce the speed much, it is safe, but this is not useful. So we should find the better speed, not too risky, not too slow. So what we are doing here is to learn from the real life. Then in Japan, we have a very big near-miss incident database, which is managed by the University of Agriculture and Technology. So we allow to use this database to extract the knowledge from the database. Then the Professor Saito has developed a simplified model to obtain the better speed. Then I will show you the example here. So the case which I showed in the last, this one, the actual vehicle speed was 35.3 kilometer per hour. But based on our analysis, the speed recommendation was a bit lower, the 22.9. So this seems a bit slow, but in this kind of situation, that would be better to attain the safety just in case. So let me summarize my presentation. Our main philosophy is that the automation does not remove the human. The human is still in the loop. So the design of the human-machine interaction is the very big issue for us to be addressed. How to design the system? We use the data from the real world. So as an example, I showed that the recommendation of the speed based on the real world data for safe driving. And we are doing this kind of research for better driving. Thank you very much. And that concludes my presentation.
Okay, thank you, the Professor Ito. Since the Professor Ito should leave after the 5 minutes, therefore, I want to accept one short question if you have now. Do you have any questions? Okay, so now that we cannot see about the question, but of course, after the final session, we will have some of the discussion of how can we mature about the collaboration or the student mobility. Therefore, after the discussion, I will tell about some of the questions to the Ito Sensei. Thank you, Ito Sensei, for your great contribution.
Thank you very much.
Okay. So the next talk will be given by the Professor Tetsuya Sakurai, the professor and the director of the AI Science Center. Today, he will talk about the a little bit summary of the Tsukuba area, the artificial intelligence research. Sakurai 先生、よろしくお願いします。
Okay, so hello, I'm Tetsuya Sakurai, and today I'd like to introduce our research center in brief. And at first, let me introduce myself. I'm a director of Center for Artificial Intelligence Research and professor of Department of Computer Science of University of Tsukuba. And my research field is mathematical algorithms. Of course, I'm developing some AI algorithms and nonlinear approximation theory. And I'd like to introduce our research center next. So our center was founded in 2017, and now we have 80 faculty members. And our research center has two divisions. One is fundamental research in AI, and another is applied research. And in fundamental research division, we have some research area, such as mathematical algorithms, machine learning, big data, cybersecurity, and so on. And recently, some professors of quantum information science joined in our research center. So the quantum computing is also important area for machine learning. And in applied research, we have some areas such as healthcare, wellness, sports, medical science, material science, and so on. And also mobility, and Professor Ito is a member of our research center. And also recently, some professor from Department of Humanities joined. And so now we are considering ethics area to deploy AI algorithms for society. So we promote interdisciplinary projects between fundamental research groups, applied research groups, and governmental entities, industry, and so on. And our important mission is human supporting AI, and to contribute to realize Society 5.0. And recently, we have AI partnership with University of Washington, and this is 10-year project and supported by NVIDIA and Amazon. And the total budget is $50 million US. And so we are promoting AI researches, collaborating with University of Washington, NVIDIA, and Amazon. And you can see this photo. And left side, it is U.S. Secretary of Commerce and Vice President and Provost of Washington University. And here is President Nagata of our university and Vice President of NVIDIA and Minister of Education, Science and Technology in Japan. Okay. And so the important keyword is Society 5.0, and it is a concept originated in Japan, and it represents the vision of a new social model. And now we are in Society 4.0. It is information society, so we can use internet, computer, and so on. And now we are shifting to next new society called Society 5.0. And here, the physical space and cyberspace. And in cyberspace, AI analyze using big data from physical space and feedback to real space. And another important concept is data free flow with trust. This concept was proposed by former Prime Minister Abe at the 2019 Davos meeting. And at that moment, he said, the engine for growth is fueled no longer by gasoline, but more and more by digital data. So data plays a key role in improving productivity and for next new society. So we are targeting on data also. And so there are many kind of AI and distributed data in real world. And we get such data and represent knowledge by some kind of abstract space. It is called latent space. And then we extract knowledge from this space and support decision making and so on. And so we are developing such algorithms. But to utilize such data, there are many difficulties. Later, Anna will introduce something about it. And it is called data science problem. And so we need to solve many difficulties to use such distributed data, such as management difficulties and confidential issues, such as privacy. So we are considering a kind of challenge using privacy-preserving machine learning. And across borders, we'd like to construct integrated AI model between some countries. So we are using federated learning, and also in local area, we apply our original method, data collaboration method, and then make such integrated AI model across borders. That's all. Thank you.
Thank you, Sakurai Sensei. So that we can catch about the many information on the broader picture of the current situation of the AI research in Japan, and also that some of the collaboration with the US company and so on. This has the many applications to field. And before accepting about this question, I will start about the next presentation. And after finishing about the whole of the presentation, we will have the discussion for the future. Okay, thank you, Sakurai Sensei. So the next speaker is Anna Sensei, and she is talking on the machine learning and artificial intelligence. Let's start.
Okay, thank you very much for the introduction. Let me share my screen. Do you see my presentation?
Yes.
Okay, great. Let me minimize this. All right. Just a second. Wait. Okay. So my name is Anna Bogdanova. I'm originally from...
Anna Sensei,
yes.
please switch about the display mode. Now that you are the presentator mode.
Okay.
So, yeah, the flip about some of the display setting.
All right, let me try again. Okay, do you see it now?
Yeah, this is the same. And you can see about the upward about some of the icon, and the right second one is the flipping about this one. Yeah, this one.
Flip this, please. Yeah.
Perfect.
It's better now?
Yeah.
That's
okay.
Perfect. Thank you.
All right. So my name is Anna Bogdanova, and I'm originally from Ukraine, but I've been living and working in Japan for quite a long time now. And I'm assistant professor at the Department of Computer Science and Center for Artificial Intelligence Research. Okay. Oh, wait. Now I cannot. Oh, all right. It worked. So I'd like to talk about some of my research interests. I work on several different projects currently, and my research interests are algorithms for privacy and fairness and explainability in machine learning, I'm particularly interested in studying their trade-offs because fairness and explainability often goes as a trade-off to privacy. And also currently I'm working some explainability algorithms for knowledge discovery in biomedical science. So first, I will talk briefly about privacy-preserving machine learning. So with current massive databases available online and very rapid rates of data collection, it's no longer sufficient to simply anonymize the data in order to protect data subjects. Because we know, and it has been shown multiple times, that with richness of anonymized data is very simple to re-identify individuals. So to find individuals that match exactly like each data point. So when you can do it, it's no longer necessary to have the individual's name or address even available or published. So this sort of re-identification hacks and attacks, they happened in the past, and we have to be very careful about publishing any kind of data, even if it's been anonymized. And one kind of solution is differential privacy. Something has been commonly used and in practice. But it's adding noise to the data so that individuals can no longer be certainly identified. But this noise adding is very often depletes the usefulness of the data. So we often have to think about some sort of trade-off there. And another approach has been distributed machine learning. And most commonly used methods is called federated learning, already was mentioned by Professor Sakurai today. But the basic principle is, instead of bringing data to the model, we bring model to the data. So the model is distributed to the users, and then users train their machine learning model locally. And after that, they only share model updates with the server. And if it's the model training done in this distributed manner, we can accomplish the training of machine learning model without ever accessing or seeing the individual's data. So this method has been very beneficial for the development of this privacy-preserving machine learning. And there are also multiple ways that we can do it. There is naive sort of averaging, when everybody just trains their own model and then all models are just averaged. So this average model is being deployed. There is a way when a certain model is just transferred from side to side, and in a manner of transfer learning, once repeated multiple cycles, in the end, we arrive at some better trained model. And then there is a classical federated learning, in which we iteratively going back and forth from clients to server, getting each time model updates. And each method has its own benefits and disadvantages. At our research center, we've been working at alternative to federated learning. We call it data collaboration. And the main idea is before doing the model training, each user creates intermediate data representation in a latent space, something that can be safely shared and centralized, yet something that doesn't contain any kind of hook to original information, that this sort of re-identification attacks can happen. And one benefit of this approach is that once the intermediate representations are created and centralized, then we have a lot of freedom at which model can be trained. And we can also do many kinds of just data analysis on these intermediate representations. And of course, our goal is to compare it to other methods, also compare it to the situation when we can do centralized learning, so simply share the data. And very often this distributed learning will have a little bit of loss compared to the centralized setting, but sometimes this distribution is lossless. So we can accomplish the distributed training as well as we would if we could centralize the data. Okay, next, moving to the explainability side. I'm particularly interested in explainability in medical science because it's very important there. A lot of modern machine learning models are very powerful in terms of prediction power, but they are less transparent. So it's very hard to say why they make this or the other predictions. So it's so-called the black box models. So in reality, in practice, even very accurate models, like we're not sure what exactly they learn from the data, and sometimes they do not learn what we think they learned. And very simple example of that you can see on the image on the left. Image classifier algorithm that was trained to classify huskies from wolves, to identify huskies and wolves, and it gives accurate results. But if a sort of explainability method is applied, we can see that the algorithm focuses mainly on the background. So the algorithm has figured out that snowy background forest usually means wolf, and green lawn usually means husky. So we can put this kind of model in practice and not even realize that it's actually flawed in the very core. And when it comes to medicine, it's even more important. There were several famous cases when even model has been deployed, like this Google Inception model to identify cancerous versus non-cancerous moles, and it was deployed in a user application, so people could do it at home. And soon the related paper and the app had to be recalled because they found out that the model was focusing on the absence or presence of the ruler. Sorry, am I running the time? The time is a problem?
No, it's okay.
Okay.
Please continue.
Yeah, so in medical science, it's very important to have explainable algorithms. And part of my research was trying to combine this distributed machine learning with explainability. And here you see a common method of explainability called SHAP. It shows you how much each of your data features contributed to the model prediction, positively or negatively. And it's very useful, especially for finding out fairness properties of the model. So, for example, if you can see that something like gender has very negative impact on model prediction regarding credit in the bank or employment, it can really easily show you that the model is not being fair and maybe something you want to fix. But so we found out that in distributed machine learning, when users apply this sort of explainability algorithm, they get conflicting explanation for the very same data sample and obviously the same model. So our goal was to try to unify their explanations so that they can be certain that they are getting correct ones. So we call this method DC SHAP, and so it helps the users to get consistent explanations for same or similar data samples. And another sector of my activities is the collaboration with National Taiwan University in the medical field, and we have a current ongoing study that tries to identify cognitive heterogeneity in cognition versus mild cognitive impairment. And we have data on 311 people. Those are the patients that attending the Center for Cognitive Development in National Taiwan University. And so there are people who are old age, starting I think age 70 and older, and they come to the center to perform different cognition-related tasks and do the tests. And so some of those subjects have mild cognitive impairment, some others have normal cognition. And our goal is to, because it's very hard to make the diagnosis like dementia or Alzheimer at the early stages of disease. So we're trying to find in an unsupervised manner what kind of groups of clusters these people are forming, to just explore this heterogeneity, because we think, we have hypothesized that those people will need special treatment. We also have recently collected some data on their brain images. We extracted free features from brain MRIs, and we try to also do some unsupervised learning on this data. And we were able to identify these 4 clear clusters that these patients are forming. And here again, this explainability comes in handy, because the unsupervised learning algorithm can only show you the clusters, but it's very hard to explain why clusters were made. So applying something like this SHAP method can tell us more about each group. And in this case, for example, this little group in red showed interesting properties, that the subjects in this group performed really well in memory tests or vocabulary-related tests, yet their brain region volume was more similar to the group of mild cognitive impairment, which probably this inconsistency in like brain features and test performance could be due to professional training of those individuals and the kind of work they did during their working days. Okay, this is the end of my presentation. Here are some publications. We'll be happy to answer your questions. Thank you very much.
Okay, thank you, Ano-sensei. And since the schedule is a little bit tight, therefore, firstly, that we want to finish about this session presentation, and then have a discussion later. Okay, thank you. And the final talk of the Tsukuba session will be given by the Professor Yutaka Shikano. He is working on the quantum information. Since before starting about the program, so I can see about the presentation from the Baja California is mainly the focus on the AI or some of the information. But recently, the quantum the information and the technology is one of the hot topic for all over the world. Therefore, I want to include about one of the professor on the quantum information. So from that viewpoint, the Professor Shikano is the professional of this field. Therefore, he can introduce about the background of his study. Okay, let's start Shikano-sensei.
Okay, thank you so much. Thank you so much for the kind introduction. Can you see that's my slide?
Yes.
Good, great. In that, I would first of all, I sincerely thanks to the kind of organization on this is the joint workshop between Baja California and the University of Tsukuba. And I'm affiliated with that since last October. I joined the University of Tsukuba, and also I'm visiting appointment at the Chapman University in Orange County in California, actually. Then this is nearby I'm familiar with Baja California in Mexico. But unfortunately, I have never gone to there. Today I'm talking about can we find that quantum mechanics by the artificial intelligence? This is my question on that from that side. Then, before going to the main talk, is this year's Nobel Prize this is a great thanks to do. That's John Hopfield and Jeffrey Hinton was received on that slide. This is because that the Hopfield network is similar to the Ising model. This is that the associated Hopfield network means on that associated memory. On that this is that how to do that in that the laser pointer is. Okay, maybe. Sorry. This side in the right top on the figure in the associated memory network is the mimic to the Ising model. Ising model is the fundamental theory of the statistical mechanics in physics. That's why they received that Nobel Prize in physics. That's and also is that this result in that emerging the field is information statistical mechanics. That's for example, that's the associated memory is machine learning, such kind of so on. That's related to the physics. That's based on the information statistical mechanics, such kind of so on. Yeah, but Ising model, solving the Ising model, that's really hard to, and the computation really hard. That's why in the 1980s, in the Richard Feynman, this is a famous physicist, is showing tells us is that nature knows that's an answer. That's why in that the Ising model is one of the phenomenological model of the material. That's the controlling on that the Ising model. Just we can solve this. Nature knows the answer. That's why it's that just the beginning of the stage of the new computation. And also in that almost same time, in the David Deutsch, in that from UK, is he listened about that digital computations, digital computing of the mechanism that he solved. Is that these guys that mean on the digital computing scientists are using the long physics. That's why he wrote the paper on the completely new approach of the quantum computation. That's why in the emerging on the field of the quantum computation. In that's the year 1985. That means on the 1985, in the next year, in 2025, in the 40 years after of the birth of that quantum computation, and also that is the same time is accidentally 100 years after of the birth of quantum mechanics actually. That's why we receiving and that we are celebrating International Year of the Quantum Science and Technology. And also this University of Tsukuba greatly contribute to the quantum mechanics actually. First of all, we have never forget to mention about it. In the Nobel laureate, our Nobel laureate is Shinichiro Tomonaga and Reo Esaki receiving on the prize on the Nobel Prize in Physics for the developing on the quantum mechanics actually. And also recently that Take Sakurai is a mention about that the quantum computation. This is also or quantum information in the field. This is really rapidly grading rapidly developing the field. That's why in that the quantum computation is in Japan is also that developing in right now. That's why in that the physicists, basically physicists on the contribution of that field. That is the why. Is that we want to know that's the limit of the computation by the law of the physics. That's for example, as you maybe know, is a Moore's law in that knowing there, that's day by day in that transistor in that sorry, number of the transistor is rapidly growing up. But unfortunately, some of the limitation is that limited. For example, in that Brennerman, in that biophysicist, is that he wrote in that so many years ago, that's almost 50 years ago, he mentioned about that theoretical limit of the computation is that 10 to the 50 bits per second per kilogram. That's one of the fundamental limit on that of that computation. But we want to know the real limit of the computation. That's why in that we are continuing on that the quantum information science and the quantum computation. In that the Tetsuya mentioned about it. Tetsuya Sakurai is initially mentioned about the Center for inside the Center for Artificial Intelligence Research. So we joined that specialty on the quantum system information, and I was including that's the specialty. And also that's the Noboru Kunihiro. He's the expertise on the crystallography, and also the Yasuhiro Takahashi. He joined that since this April, and that's he contributed to the quantum complexity. That means quantum basic computation theory, and also Yasuhiro Tokura from the viewpoint of physics point of view. That's why in that we mentioned about it. Then that's today, how to that initiated on that another Nobel laureate on that in chemistry is this year is finding the law of the physics by the data-driven rule making. And that some of that deep AlphaFold in that some of the deep learning techniques is the protein prediction is that they receive the prize. But David Baker is finding the rule of just protein design like this. Is that one of that we wanna know that how to remind the gap to that rule making on that from that data driven. That's one of the approaches in that 2009 in the Michael Schmidt and the Hot Lipson. In that he mentioned about it. He tried to do that. Is that using the two experiment. One of that very simple experiment is one of the double pendulum, and also that double spring on the problem. He tried to that experiment. He collecting the experimental data, utilizing also the experimental data. Can we solve this? Can we derive in the Newtonian equation or not? That's why is that he first tried to do. That's in that almost 15 years ago. That's they tried to do. And also very recently in the that I mentioned, I forget to mention about this year is 2021. Max Tegmark in the group in that from MIT. AI Feynman that's developing on the utilizing on that some of the network physics is inspiring methods for the symbolic regression. Is they try to do they succeeding on that 100 equation from the textbook of physics, almost in a 15 to 90%, or that means almost 70%. Is that he solved that problem? That means also data-driven science and that's finding the rule maybe, but I'm not sure. Then that's this is a problem on the quantum mechanics. For example, that's in the going back to the 19th, that's the beginning of the stage of that how to find that quantum mechanics is that you solving on the black body radiation problem. Black body radiation problem. This is the experimental data, but they are already known that the law of the physics, and that unfortunately this is unwell fit to that experimental data. But the inspiration coming from that's the Max Planck introduced that Planck constant. That's the some of this hypothesis of this. That's the some of the inspiration. That's he derived in that Planck's law. Or that's we can explain on that law of that experiment. That's the real experimental data. Finally, that's inspiration coming from that data only or not. This is one of the our case. That means that right now that's we are try to attack to such kind of problem for that utilizing the AI Feynman such and so on. That's it. In that AI, that's today's question. That the AI tells us new rules of the nature or not. That's it. In that, thank you so much for your attention.
Thank you for the wonderful talk, Professor Shikano. And before the accepting about the questions, we have to keep about the schedule. Therefore, we wanna close about this session. And later, after the session from the Baja California, we will have some of the discussion time with together. Okay. So today, so that we can have many interesting topic on the artificial intelligence and the data science, and also the quantum information and the automatic driving. So this is one of the important application for the future data-driven society. Okay, thank you for your contribution. Thank you. I want to switch about my chair role to the Baja California, the Andres, the Rivera, the Lafarga. Okay, thank you.
Much for this. We're going to.
Andres, I think the audio is just cutting off a little bit.
Is that better? Is that not cutting off?
Yes, that's better.
Excellent. Thank you. So as mentioned, Greg pointed out, thank you very much. Baja is one of the leaders in
It's still cutting off.
intelligence and quantum learning. So right now, Professor Marcela Rodriguez will go ahead from start off with the intelligence toward healthy aging.
Yeah, I think we had a little bit of issue with the audio still, but maybe you can just.
Can you hear me?
Yes, we can.
Please let me know if you see my presentation. Is that correct?
Yes, Professor. You just have to change the display. Right now you're in presentator mode. Just go ahead and select the option for swap displays on the top right of the screen.
Which options?
Swap displays.
Swap displays is on the upper left.
On the left.
Upper left, yes.
Up in the new chair, or what option?
No, in the same window, in the left, onto the left. More. It's behind the user slideshow at the left.
I cannot see.
A little bit more to the left. Right.
Here.
A little bit to the right. Just a teensy bit. Right there.
Yeah, they got it. No, the other one. Yeah, this one.
This one, the stop video, no. This one, no.
Yeah, no, the left one.
The left.
Swap display stop. Probably you must be stop the video and swap displays.
I'm going to stop the video. No, I'm going to exit. I cannot see the option. Mhm. This one is correct. Use a slideshow. Yes.
No, it's the option next to it. Swap displays.
Is that correct? My presentation? Okay, thank you. Okay, this is my presentation. Okay, thank you for the presentation. My research interests are mainly human-computer interaction, ambient-assisted living, and I use artificial intelligence techniques to implement ambient intelligence to support healthy aging. So the project that I'm going to present is a sensing system developed to collect data on driving visual behaviors. And our main motivation was that visual distractions are highly related to traffic accidents for any age group. As illustrated in this image, the relationship between age and traffic accidents follows a U-shaped curve, indicating that younger drivers and older adults are more frequently involved in accidents than middle-aged drivers. And this may be due to factors such as distracted driving, inexperience, and cognitive abilities in younger adults that may not fully developed. And on the other hand, the cognitive impairments of older adults may make their daily activities more difficult to complete, such as driving. And another important point is that aging itself does not determine risky driving. Instead, it is the physical and cognitive changes associated with aging that affect driving safety. And should stop driving due to being unfit to drive. So when we started this project, we identified that most studies analyzed the differences in visual behaviors by using cameras to collect data, which was then manually categorized by experts, which is a very time-consuming task. For instance, we found a study reporting that older drivers can scan less extensively at intersections than younger drivers. And we also realized that little attention has been paid to using sensing techniques and artificial intelligence technologies to conduct such studies. And that's why we propose a different approach and to implement an intelligent system that enabled us to infer the visual point of attention associated with vehicle cockpit zones from the pitch, yaw, and roll angles of head movements. And well, given that visual inattention is associated with poor driving performance and that cognitive abilities decline with aging, we are developing sensing technology to investigate whether visual behaviors can be reliable predictors of safe driving measures. On stage one, on the first stage of this project, we developed a multi-source intelligent sensing system to collect data during naturalistic driving sessions. And the collected data, we have used the collected data to contrast the visual behaviors of older adults and younger adults and study how these behaviors associate with driving context. During stage two, we extend the functionality of the system based on the lessons learned from the previous study. And we conducted a second study with participants, which were younger adults, 16 younger adults and 4 older adults, and validated the effectiveness of the system to collect reliable data on visual behavior properties, but also was a pilot study that enabled us to identify several instruments to assess safe driving. And we are working on generating prediction models that can predict several of these neuropsychological measures. And on stage 3, we plan to conduct further studies in order to generate more robust prediction models, since we are aware that we need more data from different participants. The measures that we are the important measures for our study are related to visual behaviors. There are two measures. One is the glance duration to visual point of attention, and the other measure is the quantity of glances to visual point of attentions. And the driving context measures are driving velocity, location, and road type. And in order to collect this data, we implemented the system with several components. One of these components is the attitude and heading reference system, which embed several inertial sensors. And we implemented a facial recognition application to sense the movement of the head. This sensor transmit the head angles via Bluetooth to the data collection application in a Google Nexus tablet. And as you can see in this slide shows that in the tablet we have components to infer the visual point of attention based on the movements of the head, and we collect data at a sampling frequency of 15 hertz. And this data can be stored in a particular repository of this tablet. We also have in this tablet components that enable us to collect data related to the driving context. One of them is through the GPS. We can collect data about the location of the drivers. And also we implemented a user interface that enables us, or an annotator, to label the inferred visual point of attention with the specific information of the driving context, such as indicating if the driver was turning to the right or left or stopped at a red light. Another component that have our sensing system is a tool based on MATLAB, which enables us to pre-process the data, such as mapping the latitude and longitude coordinates to a road name, cleaning misclassification, and estimating the duration and frequency of glances to visual point of attention. And the measures related to fitness to drive are those related to tests that, according to literature, can be used to assess the fitness to drive. We selected a battery of neuropsychological tests, which are paper-based tests, such as digit symbol substitution, MOCA, clock drawing test, trial making test part A and part B. And also we implemented computer-based instruments that enabled us to assess the simple reaction time and the peripheral reaction time. In particular, we are using a simulator to assess the peripheral reaction time. That is while the participant is driving, we present a visual stimulus, and we take measures regarding the peripheral reaction time. And finally, another measure is we are using an on-road driving test. This is a validated instrument that we implemented for a tablet in order to be used by a driving instructor who assess the errors that the driver have during the driving session. Some of our results are the following. In our study, we had in total 40 participants during stage 1 and stage 2. They met a set of inclusion criteria. 31 were younger adults and 19 were older adults. And some of our results are the following. The graph on the left suggests that older adults spend more time looking at the road than younger adults. And the graph on the middle presents that younger adults spend more time looking at the lab in contrast than older adults. And younger adults look more frequently at any of the off-road visual point of attention. At the right image shows that the visual point of attention that younger drivers are most likely to fix their eyes on are the lab and the right visual point of attention. And the lab was associated with using their mobile phones. Meanwhile, the right was related to seeing the right mirror and interacting with the passenger in the adjacent seat, who in this case was a student who was the annotator of the data. In this slide, the upper images illustrate that the number of glances on the road has a positive correlation with velocity in both groups. On the contrary, number of frequencies on road has a negative correlation with velocity, as can be seen in the lower images. We also observed differences in visual behaviors in a specific driving context. For example, younger adults use their mobile phone more frequently than older adults, particularly while driving, even more so when stopped at a red light. And this result enabled us to validate the effectiveness of our sensing technology in collecting visual points of attention, as our results align with findings reported in the literature. We have also used the visual behavior properties to generate some classification models to identify how these behaviors properties can be used to discriminate between age groups. We found that the number of frequencies directed off-road is the best predictor of the age. And finally, we also have started to understand how all these variables, visual behavior properties, neuropsychological tests, and the observation of errors made during the driving session are associated. We have found that several correlations among these studied variables. Here we emphasize the association between the EDOS score, which represent driving errors, and the simple reaction time and the peripheral reaction time. Additionally, we observed a correlation between number of glances at the road and the digit symbol substitution test, which is a measure of processing speed and memory. Some of our conclusions of this work is that, I cannot see my presentation. Okay, that we have conducted two pilot study with 40 participants that enable us to provide preliminary evidence that visual behaviors properties can be predictive of some neuropsychological measure. However, we consider that we need to increase the data set with more participants and explore additional driving and driving context measures. We are modifying the system to include another inertial sensor in order to eliminate the facial recognition application. And also we are considering including eye tracking by using some sensing technology based on electrooculography. And we consider that our sensing platform can be used also to conduct studies in different contexts to address different problems. Such, for instance, we are interested in using our platform to infer the intention of interaction and with particular applications. And I appreciate your attention for this presentation. Thank you.
Thank you very much. Appreciate that. Since we have a little bit pressed for time, we're going to proceed. Next up is Professor Ulises Orozco from CETIS University with a reinforcement learning approach for path planning in autonomous mobile robot navigation.
Thank you, Professor Andres, for the presentation. Let me share my presentation. Professor Marcela, can you start sharing your screen? Thank you. Thank you so much. Okay, can you see my presentation?
Yes.
Yes, yes.
Thank you. Hello, everyone. My name is Ulises Orozco. I'm going to present a reinforcement learning approach for path planning in autonomous mobile road navigation. The motivation for this research is based on the fact that robotics is one of the most important technologies since it is a fundamental part in automation and manufacturing process. Nowadays, these robots have jumped out of the industrial environments and are in warehouses, assistant teachers at schools, guiding people at museums, monitoring power plants, and many other applications like the amazing self-driving cars. In that sense, there is a necessity to design and develop computational models for intelligent systems. The path planning problem consists of moving the robot from point A to point B. Therefore, the environment is conceived as a two-dimensional path, which includes a set of obstacles, the configuration of the environment. The instantaneous position of the mobile robot is represented by its Cartesian coordinates and its orientation. In that way, the goal is to find a feasible sequential or sequence of configurations that can drive the mobile robot from the start position to the goal position. To address this problem, we propose the QAPF learning as a mobile robot path planning algorithm for static and non-static environments. This proposal, the QAPF, is a hybrid algorithm that makes use of reinforcement learning in a specific Q-learning with the artificial potential field method. Q-learning is a simple way to for agents, in this case the robot, to learn how to act optimally in a controlled Markovian domain. And the artificial potential field is a mathematical method for path planning proposed by Professor Suma Khatib from Stanford University. The proposed algorithm is capable to generate feasible, smooth, and safe paths for mobile robot navigation in static and non-static environments. So the contribution of this work is a new operator inside the classical Q-learning. Classical Q-learning is composed by two operators, explore and exploit. And we have proposed a new operator named APF weighting. That is a value that came from the artificial potential field that is formed from the environment. So this is the complete algorithm for the proposed algorithm. In this algorithm, we have the three operations: the exploration, the exploitation, and the APF weighting. So in a general form, the robot is initialized in any state, any random state. The process is an iterative process to find the goal. In this iterative process, if the robot collide with the obstacles or the limits of the environment, it receives a negative reward. But if it finds the goal, it receives a positive reward. So in that way, so the robot is in a current state, in some state. In that state, so if the action is to select a random action, so simply takes the neighbor in a random way. But if we select the exploitation, choose the best value from the neighbors, from the best value of Q. Q came from the Q value. So these values are updated by the Bell equation in the iterative process. When the robot achieves the goal, obtains better rewards, so we update the values with that reward. In the same case with negative rewards. And the proposed algorithm employs an artificial potential field that is composed by repulsive potential field function for the obstacles. In that way, the obstacles try to pull away the robot, and the target is composed by attractive potential field function. All the time, the target is attracting the robot to the goal point. In that way, we employ the inverse value of the artificial potential field as a probability. That probability is standardized. In that way, we select the new state or the action to the new state for the robot. Here we have some results in two kinds of environments. The first environment is an static environment. The environment it doesn't change anytime, remains static. So we can see the path found by the robot to achieve the target is the minimum, with the minimum path length. In the right side, we have another kind of environment. This environment is changing with non-static. It's a non-static environment with obstacles that in the first time the robot, it doesn't know about there. Here we have some results about the proposed algorithm versus the classic approach. The Q-learning approach is a classic approach. So the lower values are the best results. Our proposed algorithm results are in blue, and the classical approach are in red. The proposed algorithm reached an improvement of 80.83% in path length. So we have a better path in that means a shortest path to achieve the goal. An improvement of 169.75% in path smoothness for the offline mode. That means that the resultant paths are smoother. That makes better movements for the robot. And an improvement of 74.84% in training time over the classical approach. That means that the training is faster for our approach. In conclusion, this work, we have presented the QAPF, Q-learning with artificial potential field algorithm for mobile robot path planning. The proposed algorithm has demonstrated its capability to perform path planning for different static and non-static environments. To the experimental results, it has been demonstrated that the proposed algorithm is capable to give an effective and smooth path for efficient and safe mobile robot navigation. And due to the experimental results, it can be concluded that the QAPF algorithm can face more complex and bigger path planning problems. Some future work. The main problem with the classic Q-learning is that it does not scale well to large Markovian decision process. So that means that it is Q-learning shows slow convergence to the solution. A possible solution to this problem is to find a function that approximates the Q value of any state action. That can be achieved employing a neural network. Actually, this is known as a deep Q-learning. We are trying this approach using deep Q-learning or reinforcement learning that is known. This is one of the approaches that we are trying to employ. And another future work that we have is to implement this algorithm in a real robotic platform. Actually, in our university, we have some commercial robotic platforms like this one at the bottom of the left, and another one that like this aerial vehicle. But also we have built some robotic platforms in our lab by our students and collaborators, some omnidirectional robots or holonomic robots, differential wheel robots, Ackermann type robots. So we are trying different kinds of planning algorithms to to implement and find a better solution for this problem of the path planning problem. Thank you so much for your attention.
Thank you very much, Professor Ulises. I appreciate that. Next up, we'll be continuing with Professor Cesar Ortega from UTT with Big Data and Machine Learning.
Thank you. Okay, so I'm going to talk about IoT and big data, and also about a project that we have been working on. The contents of my presentation is the Internet of Things and the relationship with big data, IoT Academic Core, which it's our research group, Smart IoT Campus Project, and measuring CO2, and final comments. So Internet of Things, well, so most of you already know, it's about creating an ecosystem of connected devices that includes nodes or things with sensors that communicate to the internet. So now the abstraction is going beyond that, and they're even calling it a network of all things or web of things. So Internet of Things has lots of different applications in different fields and different industries. There's a lot of examples out there where you have devices that measure different processes, and from that, maybe actuators are turned on or off. This is, for instance, in a greenhouse. Now we have smart buildings, automated buildings, and now they include AI in some of their smart services. And industrial applications, we have Industry 4.0, which has been developing since I think 2010, where Industry 4.0 is IT intensive processing, where you have industrial IoT, where everything is connected. You have real-time data coming in, so you can take decisions with informed data. So the IoT, the reference model, the simplest way to understand it is that you have, in the physical layer, you have devices. Then you have, in the connectivity layer, you have different types of media that can connect to the web, to the internet, to the cloud. And then at the cloud level, you have edge computing, which you have a cloud platform which receives data and connects to applications where the users are. So this is the simplest way to understand Internet of Things. We have a more comprehensive model here, a 7-layer model. This is more for implementation. So as you can see, in this model, you have the physical layer at the bottom, first layer, and now you can include collaboration and processes, business processes, involve people. So now the model goes beyond just a simple application. It goes into business models. So you have a new field, which is edge computing or fog computing, which is growing rapidly because it's where you can do analytics. In the abstraction layer, you can do the same after the data is stored. So you have different examples of IoT applications. You have smart ambient systems, where you can include sensors within offices, within smart buildings, and everything is for the comfort of the workers. So when you expand all that technology, now we are going into smart cities. Well, Japan, I don't have to talk about smart cities. You have smart cities running now, expanding rapidly, where all the services are connected. You have everything is information intensive. So the Internet of Things and big data, when you try to find a relationship, well, big data refers to extremely large data sets that must include the big 5 characteristics: volume, veracity, variety, value, velocity. So if we try to understand this, well, all this information, you can process it through analytics. Later on, you can process it with machine learning. But with analytics, you can have different kinds of responses, results, predictive models, descriptive models, clustering, classification, discovery. So what is the relationship between IoT and big data? Well, IoT and big data have many overlapping components. IoT is considered a major source now of big data. So big data and IoT were developed independently, but as the volume of IoT generated data increases, you need methods to understand and comprehend what information is buried within that big data. So in a few words, devices equipped with electronics and sensors send real-time data to the Internet of Things, where it's compiled and stored, and then you can do analytics. You can find information buried within the data. So big data analytics helps make sense of gathered data by IoT devices. The solutions take vast unstructured data, organize it in smaller sets. So you can find insights into how the processes are working, so you can improve decision making. So big data, well, in industrial processes, you have metrics and you can determine the key performance indicators. From that, you can make decisions. So what trends are in big data? Well, real-time analytics, that's the trend right now. For instance, in IoT, I'm working in drip irrigation systems, for instance, measuring moisture in different fields. So you can do measurements and you can do some kind of prediction so you don't overdrip. Other challenges in data and big data analytics, for instance, is data quality. For example, in IoT, bad data quality could be due to old or noisy or faulty sensors that can't be replaced that easily. So you have to weigh in if you have a few samples that are noisy, maybe you can filter them. Maybe you can predict, maybe you can do some kind of different kinds of analytics. Well, new technologies. New technologies integration is also a challenge in big data. For instance, choosing the right tools. So the new tools and technologies can make difficult for organizations to adapt and integrate effectively. So what new technology we should watch out for? Well, edge computing, I talked about that when I showed the model, is one of the most important parts right now of end-to-end and IoT systems. Edge computing, you can do, for instance, sophisticated SQL queries. You can filter data. You can summarize it. So edge computing is a very important part, reduce redundancy, latency. So what future outlook we have? We have artificial intelligence, that's the future outlook, but big data is where you get your data sets. Also, IoT is right now starting to incorporate AI into their processes. Okay, getting to the Cuerpo Académico, this is the academic core. I'm the representative of the Internet of Things applied to production processes and services. Okay, so we have different fields of application, and we are associated, well, we have been doing different projects and sensors, networks of sensors in oyster farming. We did soil moisture monitoring for drip irrigation. So we do a lot of field work. We install different types of sensor devices and get to our platform in the cloud. So we're part of the Intel Innovation Labs network, where many institutions we're associated to develop projects. And right now we're getting into artificial intelligence. Intel donated 2 IAPCs. So we're going to start projects with them. So the important project that we're doing right now, the Smart IoT Campus, where we're creating an ecosystem of sensor nodes, measuring the environment, the air quality, dust, CO2. We have implemented some devices within the primary building where we do the experimentation, where we have alpha nodes and beta nodes. The beta nodes are the ones that right now are the ones that are giving us information, data that's relevant to our study, where we measure CO2, we measure dust, we measure different levels. And from there, we have been observing that CO2 is a very important variable. So that's our field of study right now, how to measure CO2 and to create a system that can alert the people within the building, ventilation, etc. It's an old building, so we have to implement measures that people have to collaborate. So as you can see here, CO2 levels, the levels that are okay are, for instance, the normal and low. But once you get into the high levels, above 3,000, very high, those are risk levels of contagion from indirectly from maybe somebody has COVID. So it's also a risk factor. So final comments, we're developing the Smart IoT Campus project. We're using open source resources. So because we have been using open source hardware and software, we're now developing a guide so other institutions can implement their own IoT campus, can expand it. But this could be sort of like a starting point from which you can create your own ecosystem. So thank you very much. My name is Dr. Cesar Ortega Corral, and that's my email. So if you want to contact me, thank you.
Thank you very much, Doctor. We appreciate the participation. We are going to move on a little bit more strictly due to time constraints. So next up will be Professor Mario Ramirez from the Ibero-American University with the topic of mobile robot motion control and dynamic networks and artificial vision of neural networks. Go ahead, Professor Mario.
Thank you very much for the opportunity to this presentation. I would like to introduce fast the Ibero-American University. The Ibero-American University Mexico City is the first private university in Mexico. We have more than 11,000 students, undergraduate and graduate. I would like to show this video. This video will be shown in the Grand Prix of Mexico Formula One in an stand. And I would like to show in this video all the laboratories that our university had. Will be fast. This is the design engineer laboratory. It's a physics laboratories. This is the chemistry engineer laboratories. as science of data science, engineer, laboratories. Uh, 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 Civil engineer, the laboratories. Biomedical engineer. Here we are, flying drones, mechatronics and cyber physics systems laboratories. This video will be finished really fast. It's really fast, this video. Thank you. Ready. Okay, I will continue with my presentation. Give me a second. I work in the Institute of Applied Research and Technology. I am the leader of the optimization. In this case, our main activities is to conduct inter and interdisciplinary research, fund research for projects with the university, manage the various laboratories across the campus to train new researchers and professionals. Here are websites of our laboratories. In this case, we have more than 160 laboratories. In this case, in my research, I study the activity supervision control applied to mobile robots with drones. Also, we use artificial intelligence to plan the trajectory. In this case, I will show you a video with our laboratory to synchronize 3 mobile robots using the path planning. Notice that the robots move with the maintaining keep the distance and the angle. Also, we use the disturbance text in order to keep the distance and angle. Also, our research, we use this kind of research to do that 2 mobile robots get a trajectory to manage material to manufacture planes. In this case, the robots follows a trajectory, and we develop all the dynamics models and control laws, and also planning the trajectories. Here we have some videos to our research. In this case, we can show you how the robot follows the trajectory, even the disturbance. Also, we study avoid of collisions. We study some control laws for avoid collisions. And also we study control of the trajectory planning of the drones. In this case, these videos are recent videos for our research. We synchronize two drones. Using the trajectory planning and so in this case, we have a lot of collaboration with the Ibero Tijuana, especially with Roberto Carmona. So some students comes to Ibero, Mexico City to get some course, develop thesis, develop some research, and also our students go to Ibero Tijuana to get some collaborations. So for us, it's important to share us our contact and I would like to invite you to visit us to Mexico City to Ibero-American University in order to get some collaborations or some projects. Thank you so much for this presentation.
Excellent. Thank you very much, Professor Mario. We appreciate that. Once again, we're short on time, so we will be making this a little bit quicker. Right off the bat, we're going with Professor Jesus Martinez from the Investigation Group September 16 with the development of a space mining robot as a proposal for the Artemis program missions.
Yeah, thank you very much. I'm going to show you my presentation here. Okay, is on the screen right now? Okay, thank you. My name is Jesus Rivera Martinez. I work to Grupo Educativo 16 de septiembre. In English is 16th of September Educative Group. I was 2 years ago in Osaka, Japan, working in a project on Mirai Innovation Institute. And the name of my project is a teleoperated lunar mining robot. That's a direct response to some problems in a new program named Artemis project of the NASA. So I will be very quick about because we are short of time. So in a near future, the humanity will need to exploit the moon resources. So we need to make profit about that. The main reasons to mine the moon is about helium-3. And this is because humanity needs new sources of energy. So in a near future, we need to use this kind of energy to make new kind of reactors. So the problem to solve is how about to mine the moon. Currently, mining outside our planet will be represent a very dangerous activity for future collisions. A space suit is very difficult to move on, and the conditions in the moon are very extreme. So the objective is to develop a teleoperated miner robot prototype. This prototype I was working on in Japan is only a prototype, is a proposal to solve this problem. So a teleoperated robots as a solution to the problem of exposing and carrying out mining work on the moon. So the astronauts will be able to carry out mining remotely and safely. In the near future, part of the Artemis program is to colonize the moon and to establish there some kind of settlements and bases. So a lot of scientists and astronauts will be living there. So using robots to mine the moon will be a very suitable solution to that. So the state of the art right now is the NASA since 2013 has been developing different proposals and different kind of robots to mine the moon. So this is a few proposals to that solution. So the shape of the robots are very strange. That's because the conditions in the moon are very different from here on our planet. So the adaptation of the models and the geometry of the robots is crucial to do that task. So a little background about is there is a competition called Lunabotics, which consists in the development of a remotely controlled robot with the purpose of extracting lunar regolith. So this project is entirely guided, or the purpose of that is to compete in the near future in this competition. So this is the most important part, is the Artemis program. You can search about that. This is the first step, is making prototypes to how to live on the moon. And one of the proposals is using a lot of robots to do a lot of stuff on the moon. So the first prototype of this is to use a different kind of mechanism. This is the first step, making all the entire robot teleoperated. The robot is equipped with the following mechanism. It uses a track thread system to avoid jams. The other one is to use a bucket excavation system. It's like the same system we use here in the planet, in Earth, to excavate a lot of amount of dirt. It uses an automatic anchoring system. That's because the gravity in the moon is pretty less than Earth. So the robot uses a kind of mechanisms to attach to the ground. So, and the robot also has a robot arm. That robot arm is intended to be used as a to remove some rocks and hard stuff. So this system, or this robot, is designed with a Jetson Nano. This is it's like a little computer. The purpose of this is to prepare the robot to use artificial intelligence in the near future or in the next steps of the project. The cost of this microcontroller is it's pretty cheap if you compare with entire computer system. It uses periphericals. The periphericals controls all the actuators, all the servo actuators, and all the electric motors, and is divided with a CPU that is a Jetson Nano, and the motor drivers that is the power stage of this robot. And we use TCP/IP communication. We use a antenna, a Wi-Fi antenna, but in the next prototypes is intended to use another kind of telecommunications like 5G or microwave systems. And this was the first prototype. Is a little robot like a half a meter. and about 3 kilograms. Is pretty small, but the purpose of this robot is to test the technology. And to navigate and to use the robot arm, we use another arm for navigation. The robot in the environment, the robot is equipped with a NVIDIA Jetson Nano, and the robot is fully teleoperated. It will transmit the images from through a 180-degree camera, and will be able to observe its surroundings throughout the movement. And I will skip these videos because the time we don't know. So this prototype is not in my hands. Actually, it's in Mirai Institute. The people there is working on a new improvements. So in this program, we achieved some tests. The objective was achieved, successfully test, as the robot's main function is to avoid the danger in space mining, and the design works pretty well. So for a long-term research is the next part of this project, is to integrate the autonomy functions to make the mining process more efficient. So an improvement version could participate in the following editions of NASA Lunobotics. That is the purpose of this project. And you can see our references. This is all for today. Thank you for your attention, and thank you for all the participation of all the attendees here.
Thank you very much, Professor Seuss. As a brief summary, right, we've mentioned a number of things about artificial intelligence and machine learning, its application areas for space exploration, for assisting with the aging process and making everything a little bit more accessible and means of being able to comprehend and analyze the situation. At this point, I would like to ask Professor Sakurai from Sakura University if he would like to add anything to the conversation.
Okay, so this is the final minutes that we can have the discussion for the future collaboration and cooperation. And actually, today, so I cannot think. First of all, I failed to introduce about the speaker from the space engineering, the mining by the robotics is one of the important topic for the space engineering. Therefore, I want to share about the information to these faculty members. And then the other part, and the other part, in my feeling, the artificial intelligence covered the broad area as the presented by the Tetsuya Sakurai. And we can have the many topic for the collaboration, the cooperation via the artificial intelligence. And also your case is of course, this include about the robotics and some of the sensing, but of course, the current is okay, but in future, we need to apply it to some of the network and the making some of the control system by the artificial intelligence. So and the second point is the collaboration and the student mobility. So the last session on the semiconductor that I suggest about some of the Sakura Science program that would be helpful for the making about some of the student mobility at the short term, firstly, as the first step. And then the student from the Mexico now may join to our graduate school as the students. So such kind of the student mobility will be helpful for the making the strong collaboration between the Mexico and Japan. How do you think about this point from the Mexico team?
Well, indeed, as you mentioned, student mobility is one of the main topics or one of the important points here. Right now, due to respect for the time and agenda that we do have, I will be having to cut the discussion a little bit short. Just briefly answering the points. Student mobility indeed is one of the important points. The point of view from our Mexican students and the Japanese students combining and merging into something more is definitely a very interesting prospect on that, and it will help the further development of both machine learning and artificial intelligence in this topic.
So by the way, do you have any project for the student, the collaborative project at Mexico? For example, that as for the robotics and the system engineering, the team build the project is easy to handle compared with some of the material science and semiconductor. So how is the situation of the Mexico? That I want to ask you about the point.
I really won't be able to answer that. I'm not that well investigated or versed in how the current standards are for the students and means for artificial intelligence. It's a still freshly new territory here for our students. It's been a few years since we've incorporated into the learning plans here, so it's still new territory for us.
Can I answer that question?
Yes.
Okay, well, each institution, each university has their own system for mobility. And first, they start with an agreement between the two institutions to recognize themselves. That's through our department that establishes relations with other institutions. Each university, each institution has their own way of doing things, but mostly they start with a general agreement of collaboration. And then you go to the specifics. It all depends on the collaboration you can get between professors so they can prepare students to work on project. For instance, I talked about the Smart IoT Campus, and one of the things that we're working on that is that the students develop the sensor nodes, install them, do the programming, etc. So we can start with those kinds of actions. But we have to go first with a general agreement and then with a specific agreement depending on the project. Thank you.
Yeah, regarding, yeah, Roberto, you were first, yeah. You're on mute, Roberto.
Thank you. In the case for Iberoamericana University, we have a problem that in all students can be moving about 6 months per period. That means if one student wants to study 1 semester in other place, he can do it. The only necessary condition is that that in the case that the student goes to other overseas, he needs to check that the program is similar or the same that the old program is. I think it's a good program, but depends the university. Or in our case, we can move about 6 months or short internship or whenever. Thank you.
For the general the contract, that is the 6 months is the spending about the exchange is something that like as the short-term exchange via the credit transfer. So in that case, that is the acceptable. Of course, if we can handle about some of the agreement between the two institutions. But of course, as for the graduate student case, we can handle much more the shorter one by some of the status of the special appointment, the research student or something like this, that we can have some of the system. So the point is to to build about the such kind of the mobility, we want to the confirm about the final outcome. So for example, the one undergraduate student join as the university as the master or the PhD course student. They can the mediate about some of the topic with together, and they may breach about some of the collaboration, I suppose.
Ah, that's perfect.
Yeah, and today so that we can have the panelists from the information science and technology, the Sakurai sensei, the Anna sensei, and the Shikano sensei. Do you have such kind of the idea, and do you have some of the opinion on the future prospect of the collaboration and cooperation?
Yeah, so now we found that we have some common interest, IoT, data management, robotics, and so on, related to AI and data. So maybe we had better to start some exchange of students or professors, and yeah, and then maybe we can find some details and new collaboration projects. Yeah, yes, that's all. Thank you.
Yeah, this is my same feeling. Of course, we can get the many requests of the collaboration, but the general case, so the a little bit tough to find about where is the starting point for the collaboration. In particularly for the information science technology and the robotics case, the professor has some of the specialty for the researches. That is commonly different from the other part of the studies. Therefore, this is one of the difficulty I find. As for the materials, that is okay. The material is a common one. Therefore, we can handle some of the collaboration. But as for the systems and engineering case, that we need to think about some of the strategy to make about the collaboration scheme. How do you think about Shikano sensei?
Yeah, that's actually I'm also similar feeling with with you. Then that's yeah, I have no idea on how to develop on collaboration in in the bottom up. Then as Teruaki Takeaki mentioned about it. There are no common language like that on the information science like the materials like the material science is. Then this is a fundamental problem. But that's so to develop on the information science or the technology. We need to keeping the diversity on the field. That's why there's no common language. This is a good sign for the keeping the diversity. Yeah.
Yes. So of course, each country has a different issue. Therefore, this is an important topic for the future collaboration. But to mature about such kind of the issue, that we need to build about some of the hop, step, jump. This is the scheme of the collaboration. And in my feeling, of course, if we can accept the master or the PhD, the graduate student, that is the important ambassador for the connecting about the mutual relationship with the Japan and the Mexico. This is what we feel. But the another topic is the data science case. The data case is that this data is common. And of course, the scheme is similar, but a different topic. Therefore, some of the communication that we can get about some of the issue of the exchange about the information and the encouragement of some of the new idea. This is what we feel about the point.
Thank you. Just a thought about information technology and artificial intelligence applications. Here at Baja, many companies are interested to apply artificial intelligence for smart manufacturing. So this could be another approach, maybe apply smart data science and data analytics and AI to these kind of processes. And this could be another possibility that we can implement a student exchange program for master degree and PhD to start solving these kind of issues. As the industry evolves, we get more complex defects, and these are the things that we can also offer to the industry.
Yes. The good point of the information science technology, this is the common background is similar. But as for the research topic is specific. That means about the starting of the project is easy to handle compared with the material or semiconductor sciences. For the semiconductor case, firstly, the learn about the equipment. How can we handle about the chemicals? That is a little bit tough to the overcome about the point to the next step. Therefore, this is a totally different approach that we need to handle.
Thank you. Thank you, Mr. Sakurai, for your insightful information and thoughts, and to everybody for sharing their opinions in regards of the seminar, the semiconductor and artificial intelligence. We have to move forward to close the seminar, and we would like to thank you, everybody, for your participation in today's Baja-Tsukuba collaborative seminar on semiconductors and artificial intelligence. On behalf of the Ministry of Economy and Innovation of Baja California, we extend our deepest gratitude to each of you for your engagement and contributions. Today, we had a wonderful dynamic discussions and exchange of ideas between all the panelists across the board. We also thank the Embassy of Mexico in Japan, all the representatives from Tsukuba University and the Baja California Academy, who shared their insights, which have definitely enriched our understanding in semiconductors and artificial intelligence and where these industries are heading to. The collaboration between Baja California and Tsukuba is promising for our continued innovation. And today's conversation have also helped build the ground for future partnerships and advancements. Once again, thank you all for your engagement, your participation, and enthusiasm. We look forward to continued collaboration and success for our future initiatives. With that said, we officially close this seminar. Have a wonderful day in Japan and have a wonderful afternoon in Baja California. Thank you all and have a great day.